If you like the space and learn about its curiosities, consider subscribing to the channel. We have 3 or 4 videos every week. Thank you for your attention and enjoy the video. In the ever-expanding frontier of astronomical discoveries, new findings often challenge our perceptions of the universe, sometimes shifting paradigms entirely. Recently, astronomers have uncovered phenomena that transcend our previous understanding of planetary systems, black holes, and cosmic evolution. These revelations add to the growing complexity of how we view the cosmos, suggesting that for every answer we discover, a cascade of new questions emerges. One of the most captivating recent findings involves the detection of exoplanets orbiting rogue black holes. While astronomers have long known about exoplanets orbiting stars, the concept of planets being gravitationally bound to black holes has opened a new dimension of exploration. These black hole planets, existing in the cold and dark periphery of black holes, present a radically different environment from those we've found around stars. Scientists hypothesize that such planets could form during chaotic processes, such as the collision and merger of stars or galaxies, where massive gravitational forces tear apart existing planetary systems. Planets could be captured by a black hole's gravitational pull, entering into orbits that, while stable, are devoid of sunlight and typical energy sources. These planets likely experience tidal forces far stronger than any planet in our solar system, creating surface conditions beyond the extremes we've previously imagined. Without the warmth of a nearby star, these planets might rely on internal heating, caused by the intense gravitational forces of the black hole, to maintain subsurface oceans or geothermal activity. This internal heating mechanism, though speculative, might enable the existence of exotic forms of life, potentially driven by chemosynthesis, as we see in Earth's deep ocean hydrothermal vents. If such life exists, it would challenge our conception of what environments are habitable and broaden the scope of places where life might thrive in the universe. Moreover, astronomers recently observed what they believe to be a dark exoplanet that absorbs nearly all the light that hits its surface, reflecting less than 1% of the incoming starlight. This planet, dubbed a black mirror exoplanet, is intriguing because it represents a category of planets with extreme albedo values. This raises questions about its atmospheric composition, surface material, and potential cloud structures. Some researchers speculate that such planets may have thick, soot-laden atmospheres, or perhaps they possess complex metallic compositions that trap heat and light in unusual ways. This discovery is significant because it further diversifies the types of exoplanets known to exist, highlighting the vast range of planetary conditions that can emerge across the universe. Beyond these planetary revelations, astronomers have also made strides in understanding the enigmatic forces driving fast radio bursts, FRBs, one of the most mysterious phenomena observed in the universe. These incredibly powerful bursts of radio waves originate from distant galaxies, often lasting mere milliseconds. The cause of FRBs has been a long-standing mystery, with theories ranging from highly magnetized neutron stars to extraterrestrial technology. Recently, a breakthrough observation linked a repeating FRB to a magnetar, an incredibly dense, highly magnetic neutron star located within our own galaxy. This finding suggests that at least some FRBs may originate from magnetars undergoing violent outbursts, where the release of magnetic energy generates the intense radio waves we detect across cosmic distances. Yet, the fact that many FRBs remain unexplained keeps the door open for other potential sources, including as yet undiscovered cosmic phenomena or technological signatures. In tandem with FRBs, the study of gravitational waves has continued to evolve in unexpected ways. Since the first detection of gravitational waves from merging black holes in 2015, scientists have been refining their understanding of these ripples in space-time. New detections have revealed mergers not only between black holes and neutron stars, but also of entirely new classes of objects, possibly exotic compact objects that defy easy classification. One intriguing possibility is that some of these detections might involve primordial black holes, which are hypothesized to have formed shortly after the Big Bang. If proven, These primordial black holes could provide crucial insights into the conditions of the early universe, potentially serving as the seeds of galaxy formation. Another recent surprise in the field of gravitational wave astronomy came with the observation of a black hole merger that produced a black hole far more massive than previously expected. This has raised questions about how such massive black holes could form, as they exceed the theoretical mass limits imposed by stellar evolution models. Some astronomers propose that this might be the result of successive black hole mergers, where smaller black holes combine over time, but others suggest that we may need to revisit our understanding of stellar collapse and the formation of black holes. In the realm of cosmology, scientists have been refining measurements of the universe's expansion rate, a fundamental parameter known as the Hubble constant. Interestingly, different methods for calculating the Hubble constant have yielded slightly different values, leading to what has been dubbed the Hubble tension. This discrepancy has led some researchers to propose that new physics might be required to reconcile these differences. Some hypotheses suggest that there could be unknown forms of dark energy influencing the expansion of the universe in subtle ways, or that we might need to revise our understanding of gravity at cosmological scales. The resolution of the Hubble tension could have profound implications for our understanding of the universe's fate and its ultimate structure. In parallel, investigations into dark matter, the mysterious substance that makes up roughly 85% of the universe's mass, are pushing the boundaries of particle physics and cosmology alike. Though dark matter does not interact with light, making it invisible to telescopes, its gravitational effects are observable on galaxies and galaxy clusters. Recent experiments at underground facilities have sought to directly detect dark matter particles through their rare interactions with ordinary matter. While no definitive detections have yet been made, some scientists are exploring the possibility that dark matter might interact more weakly with regular matter than previously thought, or that it could consist of entirely new kinds of particles outside the current framework of the standard model of particle physics. Perhaps the most tantalizing recent development in the study of dark matter comes from cosmological simulations, which suggest that dark matter could form dense clumps or halos on scales far smaller than entire galaxies. These microhalos could harbor pockets of dark matter so dense that they bend light, acting as natural lenses that amplify the light of distant stars or galaxies behind them. If detected, these dark matter halos would offer direct evidence of dark matter's structure on small scales and provide critical clues about its nature. In addition to these cosmic mysteries, the search for life beyond Earth continues to captivate both scientists and the public. The discovery of phosphine in the atmosphere of Venus, though still debated, has rekindled interest in the possibility of life in the most unexpected places. Phosphine is a gas associated with biological processes on Earth, leading some researchers to speculate that microbial life could exist in Venus's cloud decks, where conditions are more temperate than its hellish surface. While alternative explanations for the presence of phosphine, such as unknown chemical processes, are being actively explored, the tantalizing prospect of life in our own planetary neighborhood has spurred new missions to investigate Venus more closely. In the outer solar system, the icy moons of Jupiter and Saturn, particularly Europa and Enceladus, remain prime targets in the search for extraterrestrial life. These moons are believed to harbor vast subsurface oceans beneath their icy crusts, kept warm by tidal forces from their parent planets. Recent observations have detected plumes of water vapor erupting from Enceladus's south pole, providing a rare opportunity to sample the subsurface ocean without drilling through miles of ice. Future missions, like NASA's Europa Clipper, aim to investigate these moons in greater detail, searching for signs of life or the conditions necessary to support it. As we continue to push the boundaries of exploration and discovery, it becomes increasingly clear that our understanding of the universe is still in its infancy. Each new finding reveals not just answers, but also deeper, more complex questions. Whether we are uncovering planets orbiting black holes, probing the mysteries of fast radio bursts, or seeking the elusive particles of dark matter, the universe remains a vast and awe-inspiring puzzle. As we look further into the cosmos, we are reminded that our quest for knowledge is as boundless as the universe itself. And with every new discovery, we take one small step closer to understanding our place in the grand scheme of existence. As we delve deeper into the mysteries of the universe, the next frontier of exploration seems to lie not just in what we can observe, but in what lies hidden beyond the limits of current technology and understanding. One of the most intriguing areas of research in modern astronomy is the concept of dark galaxies. Unlike the galaxies we are familiar with, which shine brightly with the light of billions of stars, dark galaxies are almost entirely devoid of visible light. They are thought to be composed primarily of dark matter, making them invisible to conventional telescopes. However, their presence can still be inferred through their gravitational effects on nearby matter, such as by bending light from distant stars or influencing the rotation of visible galaxies. These dark galaxies, if they exist in large numbers, could be key to solving several outstanding questions in cosmology. For one, they might help explain why the universe appears to contain far more mass than we can account for with visible matter alone. Dark matter is already believed to make up the bulk of the universe's mass, but dark galaxies would provide additional evidence that we are only seeing a fraction of the true structure of the cosmos. Recent studies using radio telescopes have begun to identify potential candidates for dark galaxies, primarily through the detection of hydrogen gas that seems to be moving in ways that suggest the presence of unseen mass. These observations are still in their infancy, but they hint at a vast, hidden architecture to the universe that we are only beginning to uncover. On a much smaller scale, another area of significant progress involves the study of asteroid and cometary impacts on planets, particularly in relation to Earth's own history. New evidence suggests that ancient impacts may have played a more pivotal role in shaping the conditions necessary for life than previously thought. One particularly striking discovery involves the Chicxulub impact crater, which is widely believed to be the result of the asteroid that caused the mass extinction of the dinosaurs 66 million years ago. Recent research indicates that the aftermath of this colossal event may have created a fertile environment for the emergence of life, despite the initial devastation. When the asteroid struck Earth, it released vast amounts of energy, creating massive tsunamis, wildfires, and ejecting enormous quantities of sulfur into the atmosphere, which caused a dramatic drop in global temperatures. However, as the dust and aerosols eventually settled, new ecosystems emerged in the drastically altered environment. Some scientists now believe that such events might have acted as evolutionary resets, wiping out dominant species and creating opportunities for new forms of life to emerge. This has led to the suggestion that similar impacts on other planets, particularly Mars, might have created temporary habitable conditions in the distant past, even if those conditions were short-lived. Speaking of Mars, the ongoing exploration of the red planet continues to produce surprising results. NASA's Perseverance rover, which landed on Mars in 2021, has been drilling into the Martian surface and collecting samples from an ancient river delta in Jezero Crater. This region is believed to have been a vast lakebed billions of years ago, and the sedimentary rocks here might contain fossilized microbial life, if it ever existed. One of the most exciting findings so far has been the detection of organic molecules in the Martian soil. While these molecules alone do not prove the existence of life, they're the building blocks of life as we know it, and their presence strengthens the case for Mars having once been a more hospitable world. Looking even further afield, the search for life beyond our solar system has taken on new urgency with the discovery of several potentially habitable exoplanets. Among these, Proxima Centauri b, located just over 4 light-years away in the habitable zone of our closest stellar neighbor, continues to be a focus of intense study. Proxima Centauri b orbits its red dwarf star in a region where liquid water could potentially exist, making it one of the most promising candidates for hosting life outside our solar system. However, its proximity to a red dwarf star also poses challenges. Red dwarfs are known for their intense stellar flares, which could strip away the atmospheres of nearby planets, making them less hospitable over time. To counter these concerns, some researchers suggest that planets like Proxima Centauri b might have magnetic fields strong enough to protect their atmospheres from stellar radiation, much like Earth's magnetic field shields us from solar winds. Alternatively, life on such planets might have evolved to thrive underground or in ocean environments, where it would be shielded from harmful radiation. The James Webb Space Telescope, which is now operational, is expected to play a crucial role in studying the atmospheres of these distant worlds. By analyzing the light that passes through an exoplanet's atmosphere as it transits in front of its star, scientists can detect the presence of gases like oxygen, methane, and water vapor, potential indicators of biological processes. The detection of biosignatures on distant exoplanets would undoubtedly be one of the most groundbreaking discoveries in the history of science, but it is also fraught with challenges. Even if we detect promising signs, confirming the presence of life will require careful analysis to rule out non-biological explanations. For example, methane, a gas often associated with life, can also be produced by volcanic activity or other geological processes. Nevertheless, the potential rewards are immense, and the search for extraterrestrial life is now one of the primary goals of space exploration. In tandem with these efforts, scientists are also investigating the possibility of intelligent life elsewhere in the galaxy. The search for extraterrestrial intelligence, SETI, has recently shifted its focus from merely listening for radio signals to searching for technosignatures, indications of advanced technology beyond Earth. These could include things like artificial light on distant planets, megastructures such as Dyson spheres, hypothetical structures built around a star to capture its energy, or unusual chemical signatures in planetary atmospheres that cannot be explained by natural processes. One of the more recent developments in this field came from an intriguing signal detected by the Breakthrough Listen Initiative, a privately funded SETI project. In 2020, the team picked up a narrowband radio signal originating from the direction of Proxima Centauri. While further analysis suggested the signal was likely caused by human-made interference, it reignited public interest in the search for extraterrestrial intelligence. Such moments serve as reminders that the search for life, particularly intelligent life, is fraught with false positives and requires rigorous verification. Nonetheless, they also highlight the excitement and hope that such a discovery would bring, fundamentally altering humanity's place in the universe. As we stand on the precipice of these discoveries, it becomes clear that the universe is far more diverse and complex than we ever imagined. Whether it's the detection of planets orbiting rogue black holes, the possibility of dark galaxies, or the search for life on distant worlds, each new discovery brings with it not only answers but also deeper and more profound questions. It is this never-ending quest for knowledge that drives astronomers and scientists forward, pushing the boundaries of what we know and constantly reminding us of the vast unknowns that still await exploration. The universe, in all its complexity, remains a tantalizing enigma, one that continues to challenge our understanding and inspire wonder. As our journey through the cosmos continues, the discoveries that lie ahead seem even more profound, pushing the boundaries of what we know about both the universe and our place within it. One of the most exciting frontiers in astronomy right now is the exploration of cosmic phenomena that defy traditional models of understanding. Among these are ultraluminous supernovae, events so bright and energetic that they outshine entire galaxies for a brief period. These supernovae release staggering amounts of energy, and some are so powerful that astronomers have had to reevaluate the mechanisms behind their formation. Unlike standard supernovae, which occur when massive stars exhaust their nuclear fuel and collapse, ultraluminous supernovae seem to be driven by different processes, possibly involving highly magnetized neutron stars, known as magnetars, or even interactions between supermassive black holes and nearby stars. The extreme luminosity of these supernovae makes them excellent cosmic beacons, visible across vast distances. Some of the brightest supernovae observed are located in galaxies billions of light years away, and their study has provided crucial insights into the distant universe. One leading theory suggests that these ultraluminous events are powered by the rapid rotation of newly formed magnetars, which spin at incredible speeds shortly after their birth. This rapid rotation, combined with intense magnetic fields, could be responsible for the enormous energy output. However, the rarity of these events and their extreme conditions make them difficult to fully understand, leaving astronomers with many unanswered questions about their exact origins. Another area of recent interest is the discovery of supermassive black holes in dwarf galaxies, which challenges existing models of galaxy evolution. Traditionally, supermassive black holes were thought to form primarily in the centers of large galaxies, like our Milky Way, as a result of galaxy mergers and the accumulation of matter over billions of years. However, new observations of relatively small, faint dwarf galaxies have revealed that some of these galaxies also harbor supermassive black holes. This raises intriguing questions about how such massive objects can form in these relatively tiny galaxies, which are thought to have avoided significant mergers in their history. The presence of these black holes in dwarf galaxies suggests that the formation of supermassive black holes might occur through different pathways than previously believed. Some astronomers now theorize that these black holes could be the remnants of seed black holes that formed shortly after the Big Bang, possibly from the collapse of the first generation of massive stars. These primordial black holes would have had plenty of time to grow over the billions of years since their formation, even in the absence of major galactic mergers. If true, this could offer new insights into the early stages of black hole growth and the role of dark matter in shaping galaxy formation. Meanwhile, the study of black holes themselves has advanced significantly thanks to recent breakthroughs in technology. The Event Horizon Telescope, EHT, which famously captured the first-ever image of a black hole in the galaxy M87 in 2019, has continued to push the limits of our observational capabilities. This groundbreaking image revealed the black hole's event horizon, the point beyond which nothing, not even light, can escape, surrounded by a glowing ring of hot gas falling into the black hole. Since then, the EHT has been used to study other black holes, providing unprecedented views of these enigmatic objects. One of the most exciting results to come from the EHT project is the observation of polarized light around the black hole in M87. Polarization refers to the orientation of light waves, and it can provide important information about the magnetic fields in the region surrounding the black hole. The detection of polarized light suggests that strong magnetic fields are present near the event horizon, possibly playing a crucial role in the dynamics of the black hole's accretion disk, the swirling matter falling into the black hole. Understanding these magnetic fields could help explain how black holes power relativistic jets, beams of charged particles that are ejected at near-light speeds from the regions around black holes, often extending far into space. While black holes capture much of the public's imagination, another less visible aspect of the universe is the vast web of filaments that connect galaxies across cosmic distances. This so-called cosmic web is a large-scale structure of the universe, composed of dark matter, gas, and galaxies, and it reveals how matter is distributed on the largest scales. New surveys and simulations have provided stunning visualizations of this web, showing how galaxies are not randomly scattered, but instead follow a network of filaments that span billions of light years. At the intersections of these filaments lie massive galaxy clusters, the densest regions of the universe. Recent observations have even detected individual filaments of dark matter connecting galaxies, a feat that was once thought impossible due to the elusive nature of dark matter, which does not emit light. These filaments are thought to play a crucial role in galaxy formation, as they funnel gas and other materials into galaxies, providing the fuel necessary for star formation. The cosmic web also offers important clues about the nature of dark energy, the mysterious force that is driving the accelerated expansion of the universe. By studying the distribution and movement of galaxies within the cosmic web, astronomers hope to better understand how dark energy affects the large-scale structure of the universe. In parallel with these cosmic discoveries, scientists are making progress in understanding the physics of neutron stars, some of the densest objects in the universe. Neutron stars are the remnants of massive stars that have exploded in supernovae, leaving behind a core that is so dense that a sugar cube-sized amount of neutron star material would weigh as much as a mountain. Recent observations using space-based telescopes have revealed that neutron stars can exhibit extreme magnetic fields, which are trillions of times stronger than Earth's magnetic field. These magnetars, as they are known, are capable of producing powerful flares of X-rays and gamma rays, which can be detected across the galaxy. One of the more surprising findings about neutron stars involves the discovery of starquakes, or seismic activity on their incredibly rigid crusts. These quakes can release bursts of energy that are detectable as sudden changes in the star's rotation rate or as pulses of electromagnetic radiation. Studying these starquakes provides valuable information about the internal structure of neutron stars, which remains one of the great mysteries of modern astrophysics. Despite their small size, typically only about 20 kilometers in diameter, neutron stars contain more mass than the Sun, and understanding their internal composition could shed light on the behavior of matter under the most extreme conditions imaginable. As these discoveries unfold, the universe continues to surprise us with its complexity and richness. Each new observation or theory not only expands our knowledge, but also deepens the mystery of what lies beyond. The future of astronomy promises even more groundbreaking findings, especially as new technologies come online. The upcoming generation of space telescopes, such as the James Webb Space Telescope and the European Space Agency's Athena X-ray Observatory, will allow us to peer deeper into the cosmos and uncover phenomena that remain hidden from our current instruments. In the years to come, we may finally answer some of the biggest questions in cosmology, such as the nature of dark matter and dark energy, the origins of black holes and galaxies, and the potential for life beyond Earth. But as with all scientific endeavors, each answer will likely lead to new, even more profound questions. The universe, in all its vastness, continues to beckon us toward discovery, inviting us to explore its mysteries and uncover the fundamental truths that govern its existence. As we journey further into the unknown, the exploration of the universe continues to reveal not only distant worlds and cosmic phenomena, but also strange and unexpected insights into the very nature of reality itself. One of the most exciting recent developments in astronomy is the growing field of multi-messenger astronomy. This approach combines data from different types of cosmic signals, light, gravitational waves, and even neutrinos, to build a more complete picture of the events occurring across the universe. In the past, most of our knowledge of the cosmos came from observing light, whether in the visible spectrum or other forms such as radio waves, X-rays, and gamma rays. However, with the detection of gravitational waves and cosmic neutrinos, astronomers now have a powerful new set of tools for exploring phenomena that were previously out of reach. The detection of both gravitational waves and electromagnetic radiation from the same event, such as a neutron star merger, allows astronomers to probe these cataclysmic events in unprecedented detail. For example, the simultaneous observation of light and gravitational waves from the merger of two neutron stars in 2017 provided direct evidence that such mergers are the source of heavy elements like gold and platinum in the universe. This breakthrough heralds the dawn of a new era in astronomy, where events can be studied through multiple messengers, offering deeper insights into the underlying physical processes. Gravitational waves, which are ripples in space-time caused by massive objects accelerating through the universe, have opened up a new dimension of exploration. While the first detected gravitational waves came from the merger of black holes, which emit no light, the neutron star merger was unique in that it emitted both gravitational waves and a powerful burst of gamma rays. This event confirmed theories about the origin of short gamma ray bursts, which are some of the most energetic explosions in the universe. Neutrino astronomy, another emerging field, has also seen significant advances in recent years. Neutrinos are nearly massless particles that travel across the universe almost undisturbed by matter or radiation. They are produced in some of the most violent events in the cosmos, such as supernovae and the cores of active galaxies, and their ability to pass through matter without interacting makes them incredibly difficult to detect. However, neutrino detectors, such as the IceCube Neutrino Observatory located at the South Pole, have recently detected high-energy neutrinos from distant astrophysical sources, opening a new window into these powerful cosmic events. The combination of gravitational waves, neutrinos, and light allows astronomers to piece together a more comprehensive view of cosmic phenomena. Multi-messenger astronomy holds the promise of unlocking the secrets of the most extreme environments in the universe, such as the cores of exploding stars, the regions surrounding black holes, and the dynamics of galaxy collisions. As detectors become more sensitive, the number of detected events is expected to rise dramatically, providing a flood of new data that could revolutionize our understanding of the cosmos. Another intriguing area of study involves rogue planets, planets that do not orbit a star but instead drift through interstellar space. These planets, which may have been ejected from their parent star systems, are essentially cosmic nomads, wandering the vast stretches of space between stars. Recent discoveries suggest that there could be far more rogue planets than previously thought, with some estimates suggesting there might be as many rogue planets in our galaxy as there are stars. Detecting these planets is a challenge, as they do not emit light on their own, but gravitational microlensing, a technique that detects the bending of light from a distant star by the gravity of a foreground object, has allowed astronomers to identify several candidates. The discovery of rogue planets raises fascinating questions about their formation and potential for habitability. If these planets have thick atmospheres or subsurface oceans, they could potentially retain enough heat to support life, even in the absence of a star. Internal heat from radioactive decay or tidal forces could provide energy sources for life in these cold, dark environments. While the prospect of life on rogue planets remains speculative, the sheer number of these wandering worlds suggests that they could represent a significant fraction of the planetary population in our galaxy. Meanwhile, closer to home, the study of planetary systems within our own solar system continues to yield unexpected surprises. The moons of the outer planets, particularly Europa and Enceladus, have become prime targets in the search for life beyond Earth. Both moons are believed to harbor vast subsurface oceans beneath their icy crusts, and recent observations have detected plumes of water vapor erupting from cracks in the surface of these moons. These plumes provide a unique opportunity to sample the subsurface oceans without the need for deep drilling, and future missions, such as NASA's Europa Clipper, are expected to investigate these worlds in greater detail. The discovery of complex organic molecules in the plumes of Enceladus has further fueled speculation about the possibility of life. While no definitive evidence of life has been found, the presence of water, organic molecules, and energy sources such as hydrothermal vents makes these moons some of the most promising places in the solar system to search for life. The study of these icy moons could not only answer questions about the potential for life in our solar system, but also provide insights into the conditions that might support life on exoplanets with similar characteristics. Beyond the search for life, the exploration of the outer solar system has also revealed new insights into the formation and evolution of planetary systems. The Kuiper Belt, a region of icy bodies beyond Neptune, is home to a diverse population of small, primitive objects that provide a window into the early solar system. One of the most significant recent discoveries in this region was the New Horizons mission's flyby of Arrokoth, a Kuiper Belt object that revealed a contact binary, two objects that gently collided and stuck together. The study of Arrokoth and other Kuiper Belt objects offers clues about the processes that led to the formation of planets and the early dynamical evolution of the solar system. Further afield, the discovery of a possible ninth planet in the outer reaches of the solar system has generated intense interest among astronomers. This hypothetical planet, known as Planet 9, is believed to be several times more massive than Earth and could explain the unusual orbits of some distant Kuiper Belt objects. Although Planet 9 has not yet been directly observed, its gravitational influence appears to be shaping the orbits of objects in the outer solar system in ways that cannot be easily explained by the known planets. The search for Planet 9 continues, and its discovery would represent one of the most significant breakthroughs in our understanding of the solar system since the discovery of Neptune. At the same time, the field of exoplanet research continues to grow at a staggering pace. The discovery of thousands of exoplanets in recent years has revolutionized our understanding of planetary systems, revealing a stunning diversity of worlds, from gas giants many times the size of Jupiter to rocky planets smaller than Earth. Among the most exciting discoveries are those of potentially habitable exoplanets. worlds that orbit in the habitable zone of their stars, where conditions might be right for liquid water to exist. One of the most promising recent discoveries is the TRAPPIST-1 system, a star system located about 40 light-years away that contains 7 Earth-sized planets, 3 of which are located in the habitable zone. This compact system, with its tightly packed planets, offers a unique opportunity to study the dynamics of planetary atmospheres and the potential for life in a multi-planet system. Observations with the James Webb Space Telescope are expected to provide detailed information about the atmospheres of these planets, including the potential presence of water vapor, carbon dioxide, and other key molecules. As the search for habitable exoplanets continues, astronomers are also exploring the possibility of finding biosignatures, chemical signs of life, in the atmospheres of distant worlds. The detection of oxygen, methane, or other life-related gases in an exoplanet's atmosphere would be a groundbreaking discovery, offering the first direct evidence of life beyond Earth. While such detections remain elusive, the rapid advancements in technology and observational techniques make it increasingly likely that we will find definitive signs of life in the coming decades. Each of these discoveries, from rogue planets and icy moons to multi-messenger astronomy and the search for life on distant exoplanets, reflects the incredible progress that has been made in our understanding of the universe. Yet, with each new breakthrough, we are reminded of how much more there is to learn. The cosmos remains a vast, mysterious expanse, filled with wonders that challenge our understanding and inspire our curiosity. As we continue to explore, the universe promises to reveal even more of its secrets, drawing us ever deeper into the grand narrative of cosmic discovery. As we delve further into the enigmatic depths of space, it becomes clear that the universe is full of surprises, continually revealing phenomena that challenge our most fundamental theories. One of the most exciting recent developments in astronomy is the discovery of a class of objects that defy easy classification, what astronomers are now referring to as intermediate mass black holes. Until recently, black holes were thought to come in only 2 varieties: stellar mass black holes, formed from the collapse of massive stars, and supermassive black holes, found at the centers of galaxies and weighing millions to billions of times the mass of the Sun. The discovery of intermediate mass black holes fills a crucial gap in this spectrum, with masses ranging from hundreds to thousands of times the mass of the Sun. These black holes could provide the missing link between the smaller stellar mass black holes and their supermassive counterparts. Observing these objects has been particularly challenging because they do not emit light unless they are actively accreting matter. However, gravitational wave detectors like LIGO and Virgo have recently observed mergers involving black holes that fall into this intermediate mass range, offering the first definitive proof of their existence. The discovery of intermediate mass black holes raises several intriguing questions about their formation. One theory suggests that these black holes could form from the repeated mergers of smaller black holes in dense star clusters, gradually growing over time. Another possibility is that they are the remnants of primordial black holes formed in the early universe, before the first stars and galaxies. These ancient black holes could have played a role in seeding the formation of supermassive black holes by merging and accumulating mass over billions of years. If true, this would provide a tantalizing link to the formation of structure in the universe shortly after the Big Bang. Moving to even more extreme phenomena, a recent discovery has caused scientists to re-examine the behavior of neutron stars. Neutron stars are already known to be some of the most exotic objects in the universe, with densities so extreme that a single teaspoon of neutron star material would weigh billions of tons. However, observations of neutron stars merging, accompanied by gravitational waves and electromagnetic radiation, have revealed something entirely unexpected: the creation of objects that are even denser than neutron stars, but lighter than traditional black holes. These objects, sometimes referred to as hypermassive neutron stars, exist in a brief, unstable state before they collapse into black holes, and they may hold the key to understanding the nature of matter under extreme pressure. The detection of these transient objects has opened a new frontier in the study of matter at nuclear densities. Neutron stars are composed primarily of neutrons packed together so tightly that the familiar atomic structure of matter no longer exists. Studying these objects provides a unique opportunity to explore the behavior of matter at conditions far beyond anything achievable on Earth. By analyzing the gravitational waves and light emitted from neutron star mergers, scientists hope to gain insights into the fundamental forces that govern the behavior of matter at these extreme densities, which could, in turn, shed light on the basic building blocks of the universe. In addition to these groundbreaking observations, the study of the early universe is offering new perspectives on cosmic evolution. One of the most significant recent discoveries involves the detection of cosmic dawn, the era when the first stars and galaxies began to form, ending the so-called cosmic dark ages that followed the Big Bang. The James Webb Space Telescope, JWST, has been instrumental in probing this distant epoch, capturing the faint light from some of the earliest galaxies that existed just a few 100 million years after the Big Bang. These observations have provided unprecedented detail about the formation of the first stars, which were much larger and more short-lived than the stars that populate the universe today. These massive first-generation stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, the lightest elements created in the Big Bang. They lived fast and died young, exploding as supernovae after only a few million years. The death of these stars seeded the universe with heavier elements, paving the way for the formation of planets and more complex structures. The study of these early galaxies and stars is crucial for understanding how the modern universe came to be, including the conditions that eventually led to the formation of habitable planets. The discovery of cosmic dawn also intersects with another key mystery of the universe: the nature of dark matter and dark energy. Dark matter is thought to make up about 85% of the matter in the universe, yet it remains invisible, detectable only through its gravitational effects on galaxies and galaxy clusters. Meanwhile, dark energy, a mysterious force driving the accelerated expansion of the universe, accounts for about 70% of the universe's total energy content. Together, dark matter and dark energy dominate the cosmos, yet their true nature remains one of the most profound puzzles in science. Recent observations of the cosmic microwave background, the faint afterglow of the Big Bang, combined with data from large-scale galaxy surveys, have allowed scientists to map the distribution of dark matter on cosmic scales with unprecedented accuracy. These maps show how dark matter has shaped the structure of the universe, influencing the formation of galaxies and galaxy clusters. However, the particle or particles that make up dark matter continue to elude direct detection. Experiments designed to detect dark matter particles, whether through their interactions with ordinary matter or via indirect signals like gamma rays or neutrinos, have so far produced tantalizing hints but no conclusive results. One of the most intriguing possibilities is that dark matter could consist of an entirely new class of particles not predicted by the standard model of particle physics. These particles might interact with ordinary matter only through gravity, making them incredibly difficult to detect. Alternatively, dark matter could be composed of a range of different particles, some of which might interact weakly with normal matter, while others are completely invisible except for their gravitational effects. As scientists continue to refine their experiments and observational techniques, the discovery of the true nature of dark matter could revolutionize our understanding of the universe's composition and evolution. Meanwhile, the study of dark energy remains equally perplexing. Observations of distant supernovae, combined with measurements of the large-scale structure of the universe, suggest that dark energy is responsible for the accelerated expansion of the universe. However, the exact mechanism driving this expansion is unknown. Some theories suggest that dark energy could be a property of space itself, while others propose that it might be related to a new fundamental force that we have yet to discover. Understanding dark energy is one of the most pressing challenges in modern cosmology, as it could fundamentally alter our understanding of the fate of the universe. While these cosmic-scale mysteries capture much of the attention, advancements in our understanding of smaller-scale processes also continue to push the boundaries of knowledge. In the field of planetary science, new discoveries about the atmospheres of exoplanets are offering clues about the potential for life beyond Earth. For example, recent observations of the atmospheres of hot Jupiters, gas giant exoplanets that orbit very close to their stars, have revealed a wealth of information about atmospheric composition, temperature, and weather patterns. Some of these planets have been found to have strong winds and clouds of exotic materials, such as iron or silicon, that condense into raindrops or crystals in the intense heat of the planet's atmosphere. More significantly, the study of smaller, rocky exoplanets in the habitable zones of their stars has become a focal point in the search for life. The detection of water vapor, methane, and other potential biosignatures in the atmospheres of these planets would be a major breakthrough in the search for extraterrestrial life. The James Webb Space Telescope, with its ability to study the atmospheres of exoplanets in unprecedented detail, is expected to play a crucial role in this endeavor. The exploration of our own solar system also continues to yield surprises. For example, recent evidence suggests that Mars may have had liquid water much more recently than previously thought, with signs of episodic water flows detected in certain regions. Meanwhile, the study of icy moons like Europa and Enceladus, which are thought to harbor subsurface oceans, continues to fuel speculation about the potential for life in these alien environments. The discovery of plumes of water vapor erupting from Enceladus and possibly Europa offers a tantalizing opportunity to study the chemistry of these hidden oceans without having to drill through miles of ice. As we continue to push the frontiers of knowledge, it is clear that the universe is far more complex and dynamic than we ever imagined. Each new discovery, whether it involves black holes, dark matter, exoplanets, or the distant past of the universe, adds to the richness of our understanding while also revealing new layers of mystery. The next few decades promise to be an exciting time for astronomy and cosmology, as new technologies and observatories come online and scientists continue to unravel the secrets of the cosmos. With each new discovery, we come one step closer to understanding the fundamental nature of reality itself, even as the universe continues to inspire awe and wonder. As we journey deeper into the cosmic mysteries, the vast expanse of space continues to present unexpected discoveries that challenge our understanding of the universe. One of the most groundbreaking findings in recent years involves the study of black hole mergers and the strange phenomena they generate. Mergers between black holes, which are detected through the ripples in space-time known as gravitational waves, have revealed the presence of rogue black holes, those moving through space at incredible velocities after a merger. These runaway black holes are the result of asymmetric gravitational wave emissions during the merger process. When two black holes collide, they release gravitational waves. But if the emission is not perfectly balanced, the newly formed black hole can be kicked away from its original location. In some cases, these kicks can accelerate black holes to velocities of thousands of kilometers per second, potentially ejecting them from their host galaxies altogether. This phenomenon adds a new layer of complexity to our understanding of black hole dynamics, suggesting that some black holes might roam intergalactic space, completely isolated from any galaxy or star system. This discovery has raised important questions about the long-term fate of these rogue black holes. Could they accumulate mass by wandering through clouds of interstellar gas? Or would they remain isolated and inactive for billions of years? The detection of such rogue black holes would be challenging, as they would emit little to no radiation unless they encountered matter to consume. However, if future surveys can identify these wandering giants, it would offer unique insights into the life cycles of black holes and their influence on the larger cosmic environment. The study of gravitational waves has also led to another fascinating discovery: the existence of black hole binaries in systems where one of the black holes appears to be unusually large. These systems challenge current models of black hole formation, particularly those involving massive stars. Recent observations suggest that some of these large black holes may have formed through a process known as hierarchical merging, where smaller black holes merge repeatedly over time to form increasingly massive objects. This process could explain the existence of black holes that appear to exceed the theoretical mass limit for black holes formed directly from stellar collapse. These discoveries, coupled with the ongoing detection of gravitational wave events, have significantly expanded our understanding of how black holes interact, grow, and influence their surroundings. The ability to detect gravitational waves from merging black holes not only confirms the predictions of general relativity, but also opens a new observational window into some of the most violent and energetic events in the universe. As black hole research progresses, another surprising development has emerged from the study of stars nearing the end of their life cycles: the discovery of a new class of supernova explosions that challenge traditional models of stellar death. These so-called failed supernovae involve massive stars that collapse directly into black holes without producing the spectacular explosion typically associated with a supernova. In these cases, the star's outer layers fall inward, and instead of the star blasting its material outward into space, the entire structure collapses into a black hole in near silence. Failed supernovae are thought to occur in the most massive stars, where the gravitational collapse is so strong that even the formation of a neutron star or an explosion cannot halt the implosion. The discovery of these events provides a new explanation for certain observational gaps in the number of expected supernovae compared to the number of massive stars observed in galaxies. The existence of failed supernovae also raises the intriguing possibility that there are more black holes forming in the universe than previously thought, hiding silently within their galaxies. While black holes and their violent births command much attention, another recent discovery has turned our focus toward an unexpected phenomenon: the existence of fossil galaxies hidden within larger galactic structures. These fossil galaxies are thought to be remnants of early galactic mergers, now buried deep within the core of a larger galaxy, like hidden time capsules from the early universe. One such fossil galaxy was discovered at the center of our own Milky Way, and its identification has shed light on the history of galactic evolution. The discovery was made possible by studying the motions and compositions of stars in the galactic bulge, revealing a distinct population of stars that do not fit the typical profile of Milky Way stars. These stars are part of a smaller galaxy that merged with the Milky Way billions of years ago, contributing its mass to the growth of our galaxy. Fossil galaxies like this one provide a unique opportunity to study the conditions of the early universe, offering clues about how galaxies formed and evolved over cosmic time. This revelation of ancient galactic mergers dovetails with another major area of research: the study of ultra-diffuse galaxies. These faint, ghostly galaxies contain very few stars, but have masses comparable to much larger galaxies, thanks to their dark matter content. Ultra-diffuse galaxies are puzzling because they challenge existing models of galaxy formation. How can galaxies with so few stars remain gravitationally bound, and why do they appear so diffuse? Some researchers suggest that these galaxies may have lost most of their gas and stars during violent interactions with larger galaxies, leaving behind only a skeleton of dark matter and a few scattered stars. Others propose that these galaxies may have formed in environments with a unique balance of dark matter and gas, leading to their unusual structure. The study of ultra-diffuse galaxies has also revealed some surprising exceptions: galaxies that appear to have very little dark matter at all. These so-called dark matter-deficient galaxies are almost entirely composed of visible matter, in stark contrast to the vast majority of galaxies, where dark matter dominates. The existence of these galaxies challenges the prevailing view that dark matter is a fundamental component of galaxy formation. How these galaxies formed without significant amounts of dark matter remains an open question, and their discovery may prompt a re-evaluation of some of the core assumptions about how galaxies are structured. As astronomers continue to explore the universe at both the largest and smallest scales, new discoveries in exoplanet science have also captured the imagination of the scientific community. In particular, the detection of super-Earths and mini-Neptunes has revealed a new class of planets that do not exist in our solar system. These planets are larger than Earth but smaller than Neptune, and their diverse compositions, from rocky worlds to those with thick atmospheres, suggest a wide range of potential environments. The study of these exoplanets has raised intriguing questions about planetary formation and the conditions necessary for habitability. Some super-Earths, located in the habitable zones of their stars, could have the right conditions for liquid water on their surfaces, making them prime candidates in the search for extraterrestrial life. Recent observations with space telescopes like TESS and the upcoming missions with the James Webb Space Telescope aim to study the atmospheres of these planets in greater detail, searching for signatures of life or conditions that could support it. At the same time, the discovery of exoplanets with extreme environments has expanded our understanding of the diversity of planetary systems. Some hot Jupiters, for example, orbit so close to their parent stars that their atmospheres are being blown away by intense stellar radiation. Other planets are tidally locked, with one side perpetually facing their star and the other in constant darkness, creating extreme temperature differences. Studying these worlds provides a unique opportunity to understand how planetary systems evolve under different conditions, offering insights that could inform our search for life in more temperate environments. As we continue to discover new worlds, the question of life elsewhere in the universe remains at the forefront of scientific inquiry. One of the most tantalizing recent discoveries is the detection of phosphine in the clouds of Venus, a potential biosignature that has sparked renewed interest in the possibility of life in our own solar system. Phosphine is a gas that, on Earth, is primarily produced by biological processes, although it can also be generated through some forms of volcanic or industrial activity. The presence of phosphine in Venus's atmosphere, however, is puzzling because the planet's surface is incredibly inhospitable, with temperatures hot enough to melt lead and atmospheric pressure that would crush most life as we know it. If phosphine is truly present on Venus and is not the result of an unknown chemical process, it could point to the existence of microbial life in the planet's upper atmosphere, where conditions are less extreme. While this finding is still controversial and more research is needed to confirm it, it has reignited interest in Venus as a potential site for astrobiological study. NASA and other space agencies are now planning missions to explore Venus in greater detail, hoping to determine whether life could exist in its clouds or whether the presence of phosphine can be explained through non-biological processes. As the search for life continues, each new discovery seems to remind us how little we truly know about the universe. From runaway black holes and ultra-diffuse galaxies to mysterious super-Earths and the potential for life on Venus, the cosmos is full of surprises that challenge our understanding and inspire us to keep exploring. As new technologies and observatories come online, the coming decades promise to bring even more unexpected revelations, pushing the boundaries of science and expanding our view of the universe's complexity and beauty. As the exploration of the universe marches forward, the mysteries of space deepen, unveiling phenomena that not only defy human comprehension, but challenge even our most advanced scientific models. One of the most fascinating areas of recent study involves the discovery of strange, ultra-fast stars. Stars that seem to be racing through the galaxy at incredible speeds, far faster than any of their neighbors. Known as hypervelocity stars, these celestial objects are believed to be the result of violent gravitational interactions, most often associated with the supermassive black hole at the center of the Milky Way. Hypervelocity stars are thought to form when a binary star system, two stars orbiting each other, gets too close to the supermassive black hole at the galactic center. The immense gravitational forces can tear the pair apart, capturing one star in orbit around the black hole while ejecting the other at tremendous speeds. These stars are then flung across the galaxy, hurtling away from the center at speeds that can exceed 2 million kilometers per hour. The discovery of these stars has added a new layer of complexity to our understanding of galactic dynamics and the influence of black holes on their surrounding environment. What makes hypervelocity stars particularly intriguing is not just their speed, but their potential to tell us about the inner workings of the galaxy. By studying the paths of these runaway stars, astronomers can trace their origins back to the galactic center, allowing for a more detailed understanding of the gravitational forces at play around the supermassive black hole. These stars could also act as probes, providing insights into the distribution of dark matter in the Milky Way, as their trajectories are influenced by the invisible gravitational pull of dark matter. Moving beyond our galaxy, the detection of fast radio bursts, FRBs, has become one of the hottest topics in modern astronomy. First discovered in 2007, FRBs are incredibly brief but intense bursts of radio waves originating from distant galaxies. Despite their fleeting nature, FRBs can release as much energy in a few milliseconds as the sun emits in an entire day. The source of these powerful bursts remains a mystery, though recent studies have provided clues suggesting that at least some FRBs might be linked to highly magnetized neutron stars, known as magnetars. Magnetars are a rare type of neutron star with magnetic fields trillions of times stronger than Earth's. The intense magnetic fields can cause starquakes, violent disruptions in the crust of a neutron star, which might be responsible for producing the immense energy required for an FRB. However, this explanation does not account for all observed FRBs, some of which appear to repeat, while others are one-time events. The mystery deepened in recent years when astronomers detected an FRB from within our own galaxy, allowing for more detailed study and offering the first solid evidence linking these bursts to magnetars. While magnetars are the leading candidates for explaining many FRBs, other theories range from black hole activity to exotic phenomena like cosmic strings or even hypothetical alien technology. The latter idea, while speculative, continues to capture public imagination, and ongoing research is aimed at narrowing down the possible sources of these enigmatic signals. With new telescopes coming online, such as the Square Kilometer Array (SK), scientists are hopeful that the next decade will provide definitive answers about the origins of FRBs and their potential role in the universe's energetic events. In tandem with these high-energy discoveries, a quieter but equally captivating area of research has focused on exoplanets with conditions far different from those in our solar system. While the search for Earth-like planets often dominates headlines, the study of lava worlds has recently taken center stage in exoplanetary science. These planets, located extremely close to their parent stars, experience surface temperatures hot enough to melt rock, creating oceans of molten lava on their surfaces. One of the most well-known lava worlds is 55 Cancri, an exoplanet that orbits its star so closely that its year lasts just 18 hours. The extreme heat on this planet is thought to create a hellish landscape, with molten lava covering much of its surface and temperatures reaching up to 2,400 degrees Celsius. Observations suggest that 55 Cancri could have a thin atmosphere, likely composed of vaporized rock and metals. These hostile environments provide fascinating test cases for understanding how planets evolve under extreme conditions, offering a stark contrast to the temperate, potentially habitable worlds that are the focus of much exoplanetary exploration. Interestingly, some scientists speculate that lava worlds could provide insights into the early stages of planetary formation. Shortly after their formation, many rocky planets, including Earth, are thought to have experienced periods where their surfaces were covered in molten magma oceans. Studying lava worlds and other star systems allows scientists to examine these early conditions in real time, offering a glimpse into what the early Earth might have looked like before it cooled and solidified into the habitable world we know today. Another fascinating development in exoplanet science is the discovery of planets orbiting dead stars, particularly white dwarfs. White dwarfs are the remnants of stars like our Sun, which have exhausted their nuclear fuel and collapsed into dense, Earth-sized objects. While the intense heat and radiation from a white dwarf were thought to make it unlikely for planets to survive in close orbit, recent observations have identified at least one giant planet orbiting a white dwarf. This discovery was particularly surprising because it suggests that planets can either migrate inward or survive the violent death throes of their parent star. The discovery of planets around white dwarfs has raised new questions about the future of our own solar system. In about 5 billion years, the Sun will enter its red giant phase, expanding to engulf the inner planets, including Earth, before collapsing into a white dwarf. The study of these distant systems could provide a glimpse of what might happen to our own planetary system in the far future, offering insights into the ultimate fate of the Earth and its neighbors. While planets around white dwarfs represent a new frontier in the study of planetary systems, another surprising discovery has captured the attention of scientists studying the oldest stars in the universe. A recent survey revealed the existence of stars that are almost entirely devoid of heavy elements, indicating that they may have formed just after the Big Bang, from the primordial hydrogen and helium that filled the early universe. These stars, known as population 2 stars, are thought to be some of the first stars formed after the original population 3 stars. The very first stars ever to exist exploded as supernovae, seeding the universe with heavier elements. The discovery of population 2 stars provides valuable insights into the early stages of cosmic evolution, when the first galaxies and star clusters were forming. By studying these ancient stars, astronomers hope to learn more about the processes that governed the early universe and the conditions that led to the formation of the first galaxies. This research also ties into the broader study of galaxy formation, offering clues about how small, primordial galaxies merged and evolved into the vast, complex structures we observe today. As we continue to look back into the distant past of the universe, another area of research is beginning to take shape around the study of cosmic voids, vast, empty regions of space that contain few, if any, galaxies. These voids are some of the largest structures in the universe, stretching hundreds of millions of light years across, yet they remain largely unexplored. Recent observations have shown that these cosmic voids may be crucial to understanding the distribution of dark matter and the overall structure of the universe. Cosmic voids are not completely empty. They contain faint galaxies and a diffuse distribution of dark matter, which shapes the large-scale structure of the universe. By studying the gravitational effects of dark matter within these voids, astronomers hope to gain new insights into its properties and behavior. Some researchers even suggest that cosmic voids could act as natural laboratories for testing theories of modified gravity, which attempt to explain the universe's expansion without relying on dark matter or dark energy. As these discoveries continue to unfold, it is clear that we are only scratching the surface of what the universe has to offer. From the high-speed journeys of hypervelocity stars to the enigmatic origins of fast radio bursts, and from the hellish landscapes of lava worlds to the ancient stars that formed shortly after the Big Bang, the cosmos is a place of boundless wonder and complexity. With each new revelation, we are reminded that the universe is far stranger and more intricate than we could ever have imagined. And as our technology and understanding advance, the next great discovery may be just around the corner, waiting to challenge our perceptions once again. As our exploration of the universe continues to evolve, the discoveries we are making are pushing the boundaries of not only our knowledge, but also the very limits of what we thought possible in the cosmos. One of the most intriguing recent discoveries is the detection of super-Earths that may possess conditions entirely unlike those of our home planet. While Earth is often seen as the template for habitability, these super-Earths, rocky planets several times the mass of Earth, are presenting astronomers with a broad spectrum of potential environments, some of which challenge traditional ideas of what makes a planet suitable for life. Super-Earths are fascinating because of their diversity. Some may be water worlds, completely covered in deep global oceans, while others might have thick, crushing atmospheres made up of hydrogen or helium. The size and mass of these planets suggest that they could have strong gravity, leading to conditions that are far more extreme than anything we experience on Earth. Some super-Earths might even have volcanic activity on a scale much larger than our planet, with continuous eruptions shaping the surface and potentially providing heat for subsurface oceans, much like the icy moons of Jupiter and Saturn in our own solar system. The discovery of super-Earths located in the habitable zones of their stars, regions where liquid water could exist on the surface, has sparked a wave of excitement in the scientific community. These planets, often orbiting red dwarf stars, could be ideal candidates in the search for extraterrestrial life. However, red dwarf stars are known for their violent stellar flares, which could strip away the atmospheres of nearby planets or subject them to intense radiation. This has led scientists to explore whether super-Earths in such environments could possess magnetic fields strong enough to shield them from these flares, or if life could exist in more protected environments, like deep oceans or beneath thick atmospheres. One of the most promising super-Earths discovered in recent years is LHS 1140b, a rocky planet located 40 light-years away in the habitable zone of a nearby red dwarf star. Unlike many other exoplanets that orbit close to their stars, LHS 1140b is large and dense, suggesting it could have a thick atmosphere and possibly liquid water on its surface. Its relatively quiet host star, combined with its favorable orbit, makes it an excellent target for future observations, especially with the James Webb Space Telescope, which will allow astronomers to study its atmosphere and search for signs of life. At the same time, the study of planets far more massive than Earth, those that fall into the category of mini-Neptunes, has revealed another class of potentially habitable worlds. These planets, which are smaller than gas giants but larger than Earth, could have thick atmospheres rich in water vapor and other gases. Some scientists propose that mini-Neptunes, with their deep atmospheres and potential oceans beneath, could harbor life in environments entirely unlike anything we see on Earth. While the surface of such a planet might be inhospitable, with crushing pressures and no solid land, life could theoretically exist in the planet's upper atmosphere, where conditions might be more temperate. As the discovery of diverse exoplanets continues to grow, another significant area of research has focused on understanding planetary atmospheres, specifically the atmospheres of planets that could potentially support life. The detection of molecules like oxygen, methane, and water vapor in exoplanet atmospheres has become a key goal for astronomers, as these gases can be strong indicators of biological activity. In recent years, scientists have made significant progress in studying exoplanet atmospheres through transit spectroscopy, which involves analyzing the light from a star as it passes through a planet's atmosphere. This technique allows astronomers to determine the composition of the atmosphere and search for signs of life. In 2020, a team of astronomers announced the detection of a chemical signature that generated significant buzz in the scientific community. Phosphine, a molecule that, on Earth, is associated with biological processes, was detected in the atmosphere of Venus. Venus, with its scorching surface temperatures and acidic clouds, was long thought to be an unlikely candidate for life. However, the discovery of phosphine raised the tantalizing possibility that microbial life could exist in the planet's upper atmosphere, where conditions are less extreme. Although the detection remains controversial and alternative explanations are being explored, it has reinvigorated interest in Venus, leading to plans for future missions that will investigate the planet's atmosphere more closely. While Venus presents an unexpected potential for life close to home, the search for habitable conditions continues on Mars as well. NASA's Perseverance rover, which landed on the Red Planet in 2021, has been exploring the ancient river delta in Jezero Crater, a region that may have once supported life. Perseverance has been collecting samples of rock and soil, searching for organic molecules and other signs that Mars might have been home to microbial life billions of years ago. The most exciting aspect of this mission is that some of the samples collected by Perseverance will eventually be returned to Earth by future missions, allowing scientists to analyze Martian material in laboratories with far greater precision than is possible with robotic explorers alone. Mars has long been a focal point in the search for life, but the icy moons of the outer solar system have recently become equally compelling targets. Europa, one of Jupiter's largest moons, is believed to have a vast subsurface ocean beneath its icy crust. This ocean, warmed by tidal forces from Jupiter's gravitational pull, could harbor the conditions necessary for life. NASA's upcoming Europa Clipper mission, scheduled to launch in the 2020s, will perform detailed flybys of Europa, using ice-penetrating radar and other instruments to study the moon's surface and determine whether its ocean contains the ingredients for life. Similarly, Saturn's moon Enceladus has captured the attention of scientists after the discovery of water plumes erupting from its south pole. These plumes, which contain organic molecules, provide a direct sample of Enceladus's subsurface ocean, which is also kept warm by tidal heating. The detection of these plumes has led to speculation that Enceladus could be one of the best places in the solar system to search for extraterrestrial life. Future missions to Enceladus could attempt to sample the water directly, potentially revealing whether microbial life exists in this alien ocean. Beyond the search for life within our own solar system, the study of galaxy formation and evolution has also seen significant advancements in recent years. New surveys and simulations have provided unprecedented views of the large-scale structure of the universe, revealing the intricate web of galaxies and dark matter that form the cosmic web. One of the most surprising discoveries has been the detection of galaxies that formed much earlier in the universe's history than previously thought, challenging existing models of galaxy formation. The James Webb Space Telescope, JWST, is expected to revolutionize our understanding of these early galaxies, allowing astronomers to peer back to the first few 100 million years after the Big Bang. By studying the light from these ancient galaxies, scientists hope to learn more about the processes that led to the formation of stars, galaxies, and the first black holes. This era, known as the Cosmic Dawn, is one of the most mysterious periods in the universe's history, and JWST's observations could provide crucial insights into the conditions that shaped the modern universe. At the same time, the study of supermassive black holes has taken a dramatic leap forward with the continued observations of the Event Horizon Telescope, EHT, which famously captured the first image of a black hole in the galaxy M87 in 2019. The EHT has provided astronomers with an unprecedented view of the event horizon, the point of no return beyond which nothing, not even light, can escape. Recent observations have revealed more details about the magnetic field surrounding black holes, offering clues about how these cosmic giants power the immense jets of charged particles that shoot out from their poles at nearly the speed of light. These jets, which can extend for thousands of light years, are one of the most energetic phenomena in the universe. Understanding how they form and how black holes can generate such immense energy remains one of the central questions in modern astrophysics. The EHT's continued observations, combined with future upgrades to its array of telescopes, promise to provide even more detailed views of black holes, bringing us closer to answering these fundamental questions. As the universe continues to unveil its secrets, it is becoming increasingly clear that we are only beginning to scratch the surface of its complexities. Whether we are exploring the extreme conditions of lava worlds, studying the atmospheres of distant exoplanets, or peering into the event horizons of black holes, each new discovery brings with it the promise of even more profound revelations. With every observation, the universe grows more wondrous and strange, reminding us that the quest for knowledge is never-ending and that the cosmos still holds many mysteries waiting to be uncovered. As we continue to explore the vastness of the universe, every new discovery deepens our understanding of the cosmos, while simultaneously opening up new questions that challenge the boundaries of science. Among the most recent and exciting areas of research is the study of blazars, a type of active galactic nucleus powered by supermassive black holes. Blazars are among the most powerful sources of energy in the universe, emitting jets of high-energy particles and light that can be detected across billions of light years. What makes blazars unique is the fact that one of their relativistic jets is pointed almost directly toward Earth, making them appear exceptionally bright in the sky. Blazars are of particular interest to astronomers because they offer a direct look at the extreme physics surrounding supermassive black holes. The jets of particles emitted by blazars travel at nearly the speed of light, and studying them can provide clues about how matter behaves in such extreme environments. These jets are powered by material falling into the black hole, which spirals in at incredible speeds, heating up and emitting light across the electromagnetic spectrum, from radio waves to gamma rays. Recent observations have focused on the high-energy gamma rays emitted by blazars, which can help scientists understand the processes that drive these jets and the nature of the supermassive black holes at their cores. One of the most significant recent discoveries related to blazars is the detection of neutrinos, nearly massless subatomic particles that can travel vast distances without interacting with matter. Originating from a blazar known as TXS 0506 plus 056. This marked the first time that scientists were able to trace a high-energy neutrino back to its source, providing strong evidence that blazars are responsible for producing these elusive particles. Neutrinos are difficult to detect because they rarely interact with anything, but their detection can provide valuable information about the most violent and energetic processes in the universe. This discovery has opened a new window into multi-messenger astronomy, where scientists combine different types of cosmic signals, such as light, gravitational waves, and neutrinos, to study the universe in more detail than ever before. In parallel with the study of blazars, astronomers are also making significant progress in understanding one of the most puzzling aspects of modern cosmology: the accelerating expansion of the universe. This acceleration, first discovered in the late 1990s, is attributed to a mysterious force known as dark energy, which makes up roughly 70% of the universe's total energy content. Despite its importance in shaping the evolution of the cosmos, the nature of dark energy remains one of the greatest unsolved mysteries in science. To investigate the effects of dark energy, scientists are using large-scale galaxy surveys to map the distribution of matter across the universe. One of the most ambitious of these efforts is the Dark Energy Survey (DES), which has spent years mapping hundreds of millions of galaxies to study how their distribution and motion are influenced by dark energy. By studying the large-scale structure of the universe, astronomers can better understand how dark energy affects the expansion rate over time, potentially offering clues about its true nature. Another significant tool in the study of dark energy is the detection of baryon acoustic oscillations, BAOs, which are the remnants of sound waves that traveled through the early universe. These oscillations left imprints in the distribution of galaxies, creating a pattern that can be measured to determine how the universe has expanded over time. By comparing the size of the BAO pattern at different points in cosmic history, scientists can measure the rate of expansion and determine how it has changed, which provides crucial data for understanding dark energy. In addition to galaxy surveys, the study of distant supernovae, particularly type Ia supernovae, which serve as standard candles for measuring cosmic distances, has continued to provide important insights into dark energy. These supernovae occur when a white dwarf in a binary system accumulates enough matter from its companion star to trigger a thermonuclear explosion, creating a consistent and highly luminous event. By measuring the brightness of these supernovae, astronomers can calculate their distances and track the rate of cosmic expansion. The discovery that distant supernovae appeared dimmer than expected was the first indication that the universe's expansion was accelerating. And ongoing observations of supernovae continue to refine our understanding of this phenomenon. As dark energy research progresses, scientists are also grappling with another major mystery of the universe: the nature of dark matter. Dark matter makes up about 85% of the matter in the universe, but because it does not interact with light, it is invisible and can only be detected through its gravitational effects. Recent advances in technology have allowed for more precise measurements of dark matter's distribution, particularly through the study of galaxy clusters and gravitational lensing, where dark matter bends the light from distant objects. One of the most promising avenues for detecting dark matter is through underground experiments that aim to capture the rare interactions between dark matter particles and ordinary matter. These experiments are highly sensitive, often taking place in deep underground laboratories to shield them from cosmic radiation and other interference. While no definitive detection of dark matter particles has been made yet, each new experiment narrows down the range of possible properties that dark matter could have, bringing us closer to solving one of the most enduring mysteries of modern science. On a more local scale, new insights into the dynamics of stars within our own galaxy have shed light on the Milky Way structure and its interactions with other galaxies. In particular, the discovery of streams of stars, long, thin trails of stars stretching across the sky, has provided direct evidence of the Milky Way's past mergers with smaller galaxies. These stellar streams are the remnants of dwarf galaxies and star clusters that were torn apart by the Milky Way's gravity, and they offer a glimpse into the history of galactic evolution. The Gaia Space Observatory, launched by the European Space Agency, has played a crucial role in mapping the positions and motions of over 1 billion stars in the Milky Way with unprecedented accuracy. Gaia's data has allowed astronomers to identify previously unknown stellar streams and to create a detailed 3D map of the Milky Way, revealing its complex structure, including the presence of a vast bar-shaped region at its center and the detailed arrangement of its spiral arms. The study of these stellar streams also provides valuable information about the distribution of dark matter in the Milky Way, as the stars in these streams move under the influence of both visible matter and dark matter. One of the most surprising discoveries from Gaia's data is the presence of a large number of stars that appear to have been ejected from the center of the Milky Way at high velocities. These runaway stars are thought to have been accelerated by interactions with the supermassive black hole at the galaxy's center, providing new insights into the dynamics of the Milky Way's core. Understanding the motion of these stars can help scientists learn more about the environment around the black hole and the forces that govern the behavior of matter in this extreme region. As we continue to unravel the mysteries of the Milky Way, the study of exoplanets has also entered an exciting new phase with the discovery of planets orbiting binary star systems, planets with two suns. These circumlunar planets orbit two stars at once, much like the fictional world of Tatooine from Star Wars. The discovery of these planets has challenged traditional models of planetary formation, as the gravitational forces in binary systems can create complex and unstable environments. Despite the challenges, several circumlunar planets have been detected, including a few located in the habitable zones of their stars, where conditions might allow for liquid water. These discoveries have expanded the range of possible planetary environments and raised new questions about the potential for life in systems very different from our own. The Kepler Space Telescope played a crucial role in identifying these planets, and future missions like the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope are expected to uncover even more. As exoplanet research continues to accelerate, astronomers are increasingly focusing on the study of planetary atmospheres, particularly those of potentially habitable worlds. Recent advances in spectroscopy have allowed scientists to detect the chemical composition of exoplanet atmospheres, offering the possibility of identifying biosignatures, gases like oxygen, methane, and carbon dioxide that could indicate the presence of life. The detection of these gases on an exoplanet in the habitable zone would be a major breakthrough, providing the first direct evidence of life beyond Earth. One of the most intriguing targets for this type of research is Proxima Centauri b, the closest exoplanet to Earth, located just over 4 light-years away. Proxima b orbits its star, Proxima Centauri, in the habitable zone, and future observations with the James Webb Space Telescope could reveal whether the planet has an atmosphere and whether that atmosphere contains signs of life. The discovery of life on a planet so close to our solar system would be a momentous event, fundamentally changing our understanding of life's place in the universe. As our technological capabilities grow, so too does our ability to probe the universe in ways that were once unimaginable. From the detection of blazars and the mysterious forces driving cosmic expansion to the discovery of exoplanets and binary systems, and the search for biosignatures on distant worlds, the universe is revealing itself to be far more complex and wondrous than we ever thought possible. Each new discovery brings us one step closer to answering some of the most profound questions of existence, while simultaneously reminding us that the cosmos is full of mysteries still waiting to be uncovered. As our journey into the cosmos progresses, the universe continues to reveal breathtaking and unexpected phenomena, each discovery pushing the boundaries of human knowledge. Among the most recent and perplexing findings is the detection of ultra-long-period magnetars. Magnetars are highly magnetized neutron stars, already known for their extreme behavior. But these newly discovered ultra-long-period magnetars challenge what we thought we understood about these objects. Most magnetars are known for their rapid rotation, spinning once every few seconds or milliseconds. However, the ultra-long-period magnetars spin at a much slower rate, sometimes taking hours to complete a single rotation. The discovery of these objects is surprising because it suggests that their magnetic fields are strong enough to generate high-energy emissions even without the rapid spin that powers other magnetars. This raises new questions about the mechanisms that drive magnetar emissions and challenges existing models of how these extreme magnetic fields are generated and maintained. The discovery of ultra-long-period magnetars also has implications for our understanding of fast radio bursts, FRBs, the mysterious, intense bursts of radio waves that have captivated astronomers since they were first detected in 2007. Some scientists now believe that these magnetars could be the source of at least some FRBs. The powerful magnetic fields of magnetars could create the conditions necessary to produce the energetic bursts that we observe, even from vast distances. If this connection is confirmed, it could help explain why FRBs are so difficult to predict and why some of them repeat while others do not. In addition to their potential connection to FRBs, the discovery of these magnetars suggests that there may be many more such objects lurking in our galaxy, undetected because they emit their signals so infrequently. As astronomers refine their detection techniques and improve their ability to observe faint, sporadic emissions, we may discover that ultra-long period magnetars are far more common than previously thought, offering new opportunities to study these enigmatic objects. While magnetars continue to fascinate astronomers, the exploration of exoplanets remains one of the most dynamic areas of space research. One of the most significant recent developments in this field is the discovery of exoplanets in the Hycean class, worlds with vast oceans of liquid water beneath thick hydrogen-rich atmospheres. These planets, which are larger than Earth but smaller than gas giants like Neptune, could potentially harbor life in conditions very different from those found on Earth. Hycean planets have been identified as promising candidates in the search for extraterrestrial life because their thick atmospheres provide a stable environment where liquid water could exist. The presence of a hydrogen-rich atmosphere also means that these planets could retain heat more effectively, allowing them to remain habitable even if they orbit farther from their stars than Earth does. Some scientists believe that microbial life could thrive in the deep oceans of Hycean planets, potentially resembling the extremophiles that exist in Earth's most extreme environments, such as hydrothermal vents on the ocean floor. What makes Hycean planets particularly exciting is that they are easier to detect and study than smaller, Earth-like planets. Their larger size and thick atmospheres make them more detectable through transit methods, and their atmospheres are easier to analyze using spectroscopy. With the upcoming James Webb Space Telescope, JWST, astronomers will be able to probe the atmospheres of these planets for biosignatures, gases like methane, oxygen, or other compounds that could indicate the presence of life. In recent years, the study of exoplanet atmospheres has seen significant advancements, particularly in the detection of superpuffs, exoplanets with extremely low densities. These planets, which are often described as cotton candy planets, have masses similar to Earth, but are so bloated with gas that they appear much larger. The discovery of superpuffs challenges traditional models of planet formation, as it is unclear how such low-density planets can maintain their atmospheres without losing them to space. Superpuffs are intriguing not just because of their strange physical characteristics, but also because they offer an opportunity to study planetary evolution in extreme conditions. By analyzing the atmospheres of superpuffs, scientists hope to learn more about how planets can retain or lose their atmospheres over time, and how different types of planetary systems evolve. These studies could also help explain why some planets, like those in our solar system, have relatively thin atmospheres, while others, like superpuffs, have retained vast envelopes of gas. While exoplanet research advances at a rapid pace, our understanding of the early universe is also deepening, thanks to the study of quasars, extremely bright and distant objects powered by supermassive black holes at the centers of galaxies. Quasars are some of the most luminous objects in the universe, and they provide valuable information about the conditions that existed in the early universe, particularly during the epoch of reionization, when the first galaxies and stars formed. Recent discoveries have identified quasars that existed when the universe was less than 1 billion years old, providing a glimpse into a time when the first black holes were forming. These ancient quasars are especially important because they challenge existing models of black hole formation. The supermassive black holes that power these quasars are incredibly massive, but according to current models, there should not have been enough time for black holes of this size to form in the early universe. This suggests that either black holes can grow more quickly than we thought, or that they may have formed through a process that we do not yet fully understand. In addition to shedding light on black hole formation, quasars provide valuable information about the distribution of matter in the early universe. The light from quasars travels through vast stretches of space, passing through clouds of gas and dust on its way to Earth. By studying how this light is absorbed by these clouds, astronomers can map the distribution of matter in the early universe and learn more about how galaxies and large-scale structures formed. One of the most exciting recent discoveries in the study of quasars is the detection of gravitational waves from the merger of supermassive black holes. These gravitational waves, first predicted by Albert Einstein's theory of general relativity, are ripples in space-time caused by the acceleration of massive objects. The detection of gravitational waves from stellar mass black hole mergers has become more common since the first direct observation in 2015, but detecting them from supermassive black holes is far more challenging, given the immense scales involved. The detection of gravitational waves from supermassive black hole mergers would provide a wealth of information about how galaxies form and evolve. When galaxies merge, their central black holes are thought to combine as well, creating a single, even more massive black hole. This process releases a tremendous amount of energy in the form of gravitational waves, and detecting these waves would allow scientists to directly observe the final stages of galaxy mergers. This would help answer key questions about how supermassive black holes grow and how their mergers influence the formation of stars and galaxies. Looking even further into the future, astronomers are eagerly awaiting the launch of the Laser Interferometer Space Antenna, LISA, a space-based observatory designed to detect gravitational waves from supermassive black hole mergers and other cosmic events. LISA will be capable of detecting gravitational waves from some of the most distant and energetic events in the universe, allowing astronomers to study the behavior of black holes and other massive objects in unprecedented detail. Once operational, LISA is expected to revolutionize our understanding of black holes, galaxy formation, and the large-scale structure of the universe. As we peer further into the cosmos, we are reminded that the universe is full of wonders that continue to surprise and challenge us. From the mysterious behavior of magnetars and the strange atmospheres of superpuff exoplanets to the ancient quasars that illuminate the early universe and the gravitational waves that ripple across space-time, the discoveries we are making push the limits of human understanding. The coming years promise to be an exciting time for astronomy and astrophysics, as new telescopes and observatories come online, allowing us to explore the universe in ways that were once only imagined. Each new discovery brings us closer to answering some of the most profound questions about the nature of reality, while revealing just how much more there is to learn about the cosmos. As we venture further into the mysteries of the cosmos, each new discovery unearths a deeper layer of complexity and wonder, stretching the boundaries of our understanding. Among the latest groundbreaking revelations is the detection of cosmic filaments, gigantic threads of galaxies and dark matter that stretch across the universe, forming the scaffolding on which galaxies and clusters are arranged. These filaments are the largest known structures in the universe, spanning hundreds of millions of light years and connecting galaxy clusters across immense distances. They form part of the cosmic web, the large-scale structure of the universe that reveals how matter is distributed in vast, interconnected patterns. While the existence of these filaments has been known for some time, recent surveys have provided stunning new insights into their nature. One of the most exciting developments came with the discovery of galactic winds flowing along these filaments, moving matter across the cosmic web. These winds are driven by the activity of supermassive black holes at the centers of galaxies and are powerful enough to blow material between galaxies, enriching them with heavy elements like carbon and oxygen. This process, which is known as feedback, plays a critical role in the evolution of galaxies, regulating star formation and shaping the environment of the cosmic web. The discovery of galactic winds and cosmic filaments highlights the complex, interconnected nature of the universe. It shows that galaxies do not evolve in isolation, but are part of a larger, dynamic structure influenced by the exchange of matter and energy across vast distances. This has significant implications for our understanding of galaxy formation and evolution, suggesting that the fate of individual galaxies is closely linked to the cosmic web that surrounds them. One of the tools that has been instrumental in mapping these cosmic filaments is the study of gravitational lensing. This phenomenon occurs when the gravity of a massive object, such as a galaxy cluster, bends the light from more distant objects behind it, magnifying and distorting their appearance. By analyzing the distorted light, astronomers can create detailed maps of the distribution of dark matter, which makes up the majority of the mass in these filaments but does not emit or absorb light. Gravitational lensing has provided one of the clearest pictures yet of how dark matter shapes the large-scale structure of the universe, revealing the intricate patterns of the cosmic web in unprecedented detail. The study of cosmic filaments has also led to the discovery of galaxies hidden in plain sight. Galaxies that are enshrouded in thick clouds of dust and gas, making them difficult to detect using visible light. These dark galaxies are thought to be in an early stage of formation, where they are rapidly accumulating gas and dust, but have not yet formed many stars. Observations with radio telescopes and infrared detectors have revealed these elusive galaxies, offering a rare glimpse into the process of galaxy formation at its earliest stages. Dark galaxies may hold the key to understanding how the first galaxies formed and how they evolved into the vast systems of stars we see today. At the same time, another profound discovery has emerged from the study of galaxy clusters: the detection of dark galaxies within these clusters. These are galaxies that contain little or no visible matter, consisting almost entirely of dark matter. Their discovery challenges current models of galaxy formation, which rely on the presence of gas and stars to form galaxies. Dark galaxies are thought to be the remnants of small galaxies that have had their gas and stars stripped away by interactions with larger galaxies, leaving behind only their dark matter halos. The discovery of dark galaxies raises new questions about the role of dark matter in galaxy formation. How do these galaxies evolve, and what role does dark matter play in shaping their structure and behavior? The detection of dark galaxies also provides a new way to study dark matter itself, offering a unique laboratory for probing its properties and distribution on smaller scales. While these cosmic-scale discoveries reshape our understanding of the universe's large-scale structure, new breakthroughs are also taking place much closer to home, particularly in the study of our own solar system. One of the most exciting recent developments is the confirmation of water ice on the Moon's surface, particularly in permanently shadowed regions near the lunar poles. This discovery has profound implications for future human exploration, as water is a critical resource that could support sustained human presence on the Moon and serve as a stepping stone for missions to Mars and beyond. NASA's Artemis program, which aims to return humans to the Moon by the mid-2020s, is planning to explore these water-rich regions, potentially using the ice to produce oxygen and fuel for rockets. The presence of water ice on the Moon could dramatically reduce the cost and complexity of future lunar missions, as astronauts would no longer need to bring all of their water and fuel from Earth. Instead, they could live off the land, using the Moon's resources to support longer missions and deeper space exploration. The discovery of lunar ice has also sparked interest in the broader question of water in the solar system. Recent missions to Mars have confirmed that the red planet once had liquid water on its surface, and evidence suggests that large amounts of water ice still exist beneath the Martian soil. The European Space Agency's ExoMars mission and NASA's Perseverance rover are currently searching for signs of past life on Mars, focusing on regions where water may have existed. If life ever existed on Mars, it likely would have relied on liquid water, and the discovery of microbial fossils or organic molecules would represent one of the most significant breakthroughs in the search for life beyond Earth. In addition to Mars, the icy moons of Jupiter and Saturn, Europa and Enceladus, are also prime targets in the search for extraterrestrial life. Both moons are believed to harbor subsurface oceans beneath their icy crusts, and recent observations have detected water vapor plumes erupting from Enceladus's surface. These plumes provide a direct sample of the Moon's subsurface ocean, allowing scientists to analyze its composition and search for signs of biological activity. Future missions, such as NASA's Europa Clipper, will investigate these moons in greater detail, potentially revealing whether life could exist in the dark hidden oceans of the outer solar system. While the search for life on other worlds captures the imagination, scientists are also making exciting discoveries about the origin of life here on Earth. Recent research into the chemistry of early Earth has provided new insights into how the first life forms may have arisen from simple organic molecules. One of the most intriguing discoveries is the potential role of RNA world scenarios, where RNA, a molecule similar to DNA, may have been the first self-replicating molecule to emerge on early Earth. RNA can both store genetic information and catalyze chemical reactions, making it a strong candidate for the precursor to life. New experiments have shown that under the right conditions, RNA molecules can form spontaneously from simple building blocks, suggesting that the emergence of life may have been more likely than previously thought. These findings have implications for the search for life on other planets, as they suggest that life could arise in environments where the right chemical ingredients are present, such as on Mars or Europa. As we continue to search for life beyond Earth, the study of exoplanets remains one of the most exciting areas of research. Recent discoveries have identified several exoplanets in the habitable zone of their stars, where conditions could allow for liquid water to exist on their surfaces. One of the most promising of these planets is Proxima Centauri b, located just over 4 light-years away in the habitable zone of the closest star to our solar system. While Proxima b is subject to intense stellar flares from its red dwarf star, it remains one of the most exciting targets in the search for life due to its proximity and potential habitability. The James Webb Space Telescope, JWST, set to launch soon, will be instrumental in studying the atmospheres of potentially habitable exoplanets like Proxima b. JWST's advanced instruments will allow astronomers to analyze the composition of exoplanet atmospheres and search for biosignatures, gases like oxygen, methane, and carbon dioxide that could indicate the presence of life. If these gases are detected, it would represent a major breakthrough in the search for life beyond Earth, offering the first concrete evidence of biological activity on another planet. As we look to the future, the rapid advancements in astronomy and space exploration promise to unlock even more of the universe's secrets. From the cosmic web that connects galaxies across the universe to the icy moons of the outer solar system and the potential for life on distant exoplanets, the discoveries we are making today are just the beginning. The next generation of telescopes, spacecraft, and experiments will allow us to explore the universe in ways that were once unimaginable, bringing us closer to answering some of the most profound questions about the nature of life, the origin of the cosmos, and our place in it. Each new discovery reminds us of how vast, complex, and wondrous the universe is, and how much there is still to learn. As we push the boundaries of exploration, we are not only uncovering the mysteries of the cosmos, but also deepening our understanding of the fundamental forces that shape everything around us, from the smallest particles to the largest structures in the universe. The journey has just begun, and the discoveries yet to come are sure to be even more astonishing. As we delve deeper into the vast cosmos, the universe reveals more of its intricate and often mysterious workings, offering astonishing insights into realms we had not previously imagined. One of the most fascinating recent discoveries revolves around an entirely new class of objects known as black hole stars. These hypothetical but highly plausible objects are believed to have existed in the early universe and represent a new and intriguing stage in cosmic evolution. Black hole stars, as their name suggests, are a fusion of two of the most powerful celestial objects, black holes and massive stars. These stars could have existed during the universe's early stages, when the first-generation stars, known as population 3 stars, were forming. These stars would have been much larger than any stars we see today, perhaps hundreds of times the mass of the Sun. In this theoretical model, as the core of these massive stars collapsed, instead of merely forming a black hole and ending the life of the star in a supernova, the star could continue to feed the black hole at its core, causing it to grow while still being surrounded by the stellar material. What makes these black hole stars so extraordinary is that they could shine as brightly as entire galaxies and, for a brief period, represent a stage in the universe where black holes rapidly grew in size by continuously devouring their stellar envelopes. Eventually, the star would completely collapse into the black hole, leaving behind a massive black hole much larger than anything that could have formed from the collapse of a regular star. These black hole stars, if they existed, could help explain how supermassive black holes, some of which were already fully formed in the early universe, came to be. The discovery of supermassive black holes at the centers of ancient galaxies just a few hundred million years after the Big Bang has long puzzled astronomers because there hasn't been enough time for black holes to grow to such sizes through conventional means. If black hole stars did indeed exist, they could offer a plausible explanation for the rapid growth of these early cosmic giants, accelerating the formation of the supermassive black holes that power quasars and govern the dynamics of galaxies. The study of black hole stars remains largely theoretical, but future telescopes like the James Webb Space Telescope, JWST, could potentially provide indirect evidence by observing the remnants of these stars in the form of unusually massive black holes in the distant universe. While we ponder the enigmatic beginnings of black holes, another frontier of discovery has emerged around the mysterious substance that makes up the vast majority of the universe's mass: dark matter. Despite decades of study, dark matter remains one of the most elusive components of the universe, detectable only through its gravitational influence on galaxies and galaxy clusters. However, recent research has suggested that dark matter might play an even more active role in the early universe than previously thought. One of the leading theories is that dark matter may have helped trigger the formation of the first stars. Known as dark stars, these hypothetical objects would have formed in regions where dark matter was particularly dense, allowing dark matter particles to interact and annihilate each other, releasing energy in the process. Instead of relying on nuclear fusion like normal stars, dark stars would be powered by dark matter annihilation, making them extremely long-lived and much larger than typical stars. These dark stars could have played a crucial role in the formation of the first galaxies, as their massive size and long lifespans would have influenced the distribution of matter in the early universe. Though no dark stars have yet been detected, astronomers are searching for evidence of them in the form of ancient, unusually large stars or by studying the distribution of matter in the earliest galaxies. If dark stars existed, they would offer a tantalizing glimpse into how dark matter interacts with normal matter and how it shaped the early universe's evolution. Another area of intense research in the study of dark matter involves the search for dark matter halos, regions of space where dark matter is concentrated. These halos are thought to surround galaxies and provide the gravitational scaffolding that holds galaxies together. Without dark matter halos, galaxies would not have enough mass to prevent their stars from flying apart. The search for dark matter halos is not only about understanding the distribution of dark matter, but it could also help solve one of the biggest mysteries in cosmology: why galaxies seem to rotate at constant speeds, even at their outer edges where there should be less mass. Recent studies using gravitational lensing, where light from distant galaxies is bent by the gravity of intervening dark matter, have allowed astronomers to map the distribution of dark matter halos around galaxies. These maps have revealed that dark matter is much more widely distributed than previously thought, extending far beyond the visible boundaries of galaxies. By studying how dark matter halos evolve over time, astronomers hope to gain new insights into how galaxies form and grow, and how dark matter influences the large-scale structure of the universe. While dark matter remains elusive, scientists are also making progress in the study of another cosmic mystery: gravitational waves. Since the first detection of gravitational waves in 2015, a steady stream of new discoveries has transformed our understanding of the universe's most violent events, such as the mergers of black holes and neutron stars. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, and they provide a completely new way of observing the universe, complementary to traditional electromagnetic observations. In recent years, astronomers have detected gravitational waves from some unexpected sources, including the merger of objects that defy easy classification. One of the most surprising discoveries involved the merger of a black hole with an object that was either an unusually massive neutron star or a black hole much smaller than previously detected. This mass gap object challenges our understanding of stellar evolution, as it falls into a range where no compact objects were expected to form. Understanding the nature of these mass gap objects could shed light on the processes that create black holes and neutron stars and how they evolve over time. Gravitational wave astronomy is still in its infancy, but the potential for new discoveries is immense. Future gravitational wave detectors, both on Earth and in space, will be able to detect waves from even more distant and energetic events, such as the mergers of supermassive black holes or the collisions of neutron stars with black holes. These observations could help answer key questions about the nature of black holes, neutron stars, and the formation of galaxies in the early universe. Looking even further ahead, the upcoming Laser Interferometer Space Antenna, LISA, will revolutionize our ability to detect gravitational waves from supermassive black hole mergers. Scheduled for launch in the 2030s, LISA will be able to detect gravitational waves with much longer wavelengths than ground-based detectors like LIGO and Virgo, allowing it to observe the mergers of supermassive black holes in the centers of galaxies. These observations will provide direct insights into how galaxies grow and evolve through mergers, and how the largest black holes in the universe interact with their surroundings. As we push deeper into the unknown, our understanding of exoplanets continues to advance, with new discoveries offering tantalizing possibilities for life beyond Earth. One of the most exciting recent developments is the discovery of rogue planets. Planets that do not orbit a star, but instead drift through space, untethered to any solar system. These rogue planets are believed to have been ejected from their parent star systems during the chaotic process of planetary formation, and recent studies suggest that there could be billions of them in our galaxy alone. The discovery of rogue planets has profound implications for the search for life beyond Earth. While these planets would be extremely cold due to the absence of a nearby star, it is possible that some rogue planets could retain enough internal heat from radioactive decay or tidal forces to maintain subsurface oceans of liquid water. If life can exist in such environments, rogue planets could represent a new class of potentially habitable worlds, expanding the range of places where life might thrive. One of the most remarkable discoveries in recent years is the detection of a rogue planet with a mass similar to Earth, located relatively close to our solar system. This planet, known as OGLE 2016 BLG 1928, was discovered using a technique called gravitational microlensing, which occurs when a planet passes in front of a distant star and its gravity bends and magnifies the star's light. While it is unlikely that this particular rogue planet harbors life, its discovery suggests that there could be many more Earth-sized rogue planets waiting to be found. As we continue to explore the universe, the discoveries we are making are transforming our understanding of everything from the smallest subatomic particles to the largest structures in the cosmos. From the possible existence of black hole stars and dark stars to the study of dark matter halos and the detection of gravitational waves from previously unknown objects, the universe is revealing itself to be far more dynamic and complex than we ever imagined. The next generation of telescopes, detectors, and space missions will allow us to peer deeper into the cosmos than ever before, offering new opportunities to explore the most fundamental questions of existence. Each new discovery brings us closer to answering some of the biggest questions in science. How did the universe begin? How do galaxies and stars form and evolve? And perhaps most importantly, are we alone in the universe? The exploration of the cosmos is a never-ending journey, and with each step forward, we uncover new mysteries that inspire us to keep looking further and asking deeper questions. As the universe continues to surprise and challenge us, the search for knowledge becomes even more exciting, promising discoveries that could change the way we see the world and our place in it. As we push the frontiers of space exploration and our understanding of the cosmos, the universe continues to surprise us with phenomena that seem stranger than fiction. One of the most fascinating and recent discoveries revolves around quark stars, a theoretical type of stellar remnant that could lie between neutron stars and black holes. While neutron stars are incredibly dense, so dense that protons and electrons merge to form neutrons, quark stars are thought to be even more extreme, composed entirely of quarks, the fundamental particles that make up protons and neutrons. Quark stars, if they exist, would be formed when the pressure inside a neutron star becomes so intense that the neutrons themselves break down into their constituent quarks. This would create an ultra-dense object that could be even smaller and more massive than a typical neutron star, but without collapsing into a black hole. The existence of quark stars has long been speculative, but recent observations of unusually small, dense neutron stars have rekindled interest in these exotic objects. If quark stars are confirmed, they would represent a new state of matter, unlike anything we've observed before. The study of quark stars also has profound implications for our understanding of the early universe, where conditions of extreme density and temperature may have allowed quark matter to exist. Some scientists believe that during the first few microseconds after the Big Bang, the universe was filled with a quark-gluon plasma, a hot, dense soup of quarks and gluons, which later cooled to form protons and neutrons. Understanding quark stars could therefore provide valuable insights into the physics of the early universe and the fundamental forces that govern the behavior of matter under extreme conditions. While the existence of quark stars remains unproven, advances in astrophysical research could soon offer answers. The detection of gravitational waves from neutron star mergers, for example, offers a new way to study the behavior of matter in extreme environments. If quark stars are involved in such mergers, their unique signatures could be detected in the gravitational wave signals, providing direct evidence of their existence. The upcoming generation of gravitational wave detectors, such as the Einstein telescope, will be far more sensitive than current instruments, making it possible to study these extreme objects in greater detail. In tandem with this, recent breakthroughs in nuclear physics have also advanced our understanding of the internal structure of neutron stars and the possibility of quark matter. Experiments using particle colliders, such as the Large Hadron Collider, LHC, have created conditions similar to those found in neutron stars, allowing scientists to study how quarks and gluons behave under extreme pressure. These experiments could help scientists understand whether quark matter can exist stably inside neutron stars and what conditions might trigger the formation of a quark star. While quark stars remain an exciting theoretical possibility, another profound and less speculative area of research involves the discovery of super-Earth exoplanets in the search for life beyond Earth. Super-Earths are rocky planets larger than Earth, but smaller than Neptune, and they are emerging as some of the most common types of planets in the galaxy. These planets could have conditions suitable for life, and their diversity makes them key targets for future exploration. One of the most exciting aspects of super-Earths is their potential to retain thick atmospheres, which could support stable, long-term climates. Some of these planets may have vast oceans, possibly thousands of kilometers deep, providing an environment where life could thrive. Other super-Earths could have dense, steamy atmospheres or volcanic activity, which could drive complex chemical reactions, perhaps similar to the processes that gave rise to life on Earth billions of years ago. A particularly intriguing super-Earth, known as LHS 1140b, was discovered orbiting a star located about 40 light-years away. LHS 1140b resides in the habitable zone of its star, where conditions could allow liquid water to exist on its surface. This planet is more massive and larger than Earth, which means it could retain a thicker atmosphere and possibly support life. Upcoming observations with the James Webb Space Telescope, JWST, will be able to analyze the planet's atmosphere and determine whether it contains key gases like oxygen, methane, and carbon dioxide, which could indicate biological activity. While the discovery of super-Earths continues to drive excitement, another class of planets has captured scientists' attention: exomoons. Although thousands of exoplanets have been discovered, the detection of moons orbiting these planets, known as exomoons, has proven to be much more challenging. However, recent advancements in observational techniques are bringing us closer to confirming the existence of these moons, and the implications are profound. Exomoons, like their planetary counterparts, could be prime candidates for habitability. Moons of gas giants, similar to Jupiter's Europa or Saturn's Enceladus in our own solar system, could have subsurface oceans beneath icy crusts, potentially providing environments where life could exist. In fact, many scientists believe that moons may outnumber planets as habitable environments in the galaxy. and finding the first exomoon could open a whole new frontier in the search for life beyond Earth. Recent evidence suggests the first possible exomoon was detected around a planet orbiting the star Kepler 1625. This exomoon, if confirmed, would be a massive object, potentially the size of Neptune, orbiting a Jupiter-sized planet. The discovery of such a large moon would challenge our understanding of how moons form and evolve, as it suggests that moons can grow to sizes far larger than previously thought. This finding raises the possibility that many gas giants in other star systems could have large moons, some of which might be more hospitable to life than the planets they orbit. The search for exomoons, along with the study of super-Earths, represents just one aspect of the broader effort to understand planetary systems across the universe. Another exciting area of research involves the detection of planetary migration, the movement of planets from their original formation locations to new orbits over time. This process, which is believed to have occurred in our own solar system, can dramatically reshape planetary systems, potentially bringing planets closer to or farther from their host stars. Recent discoveries have shown that hot Jupiters, giant gas planets that orbit extremely close to their stars, likely migrated inward from much farther out in their systems. These migrations could have profound effects on the other planets in the system, possibly leading to the ejection of smaller, rocky planets or causing them to collide with each other. Understanding planetary migration is crucial for explaining the diversity of planetary systems we observe and for predicting where habitable planets might be found. At the same time, the search for habitable worlds has expanded to include not only planets orbiting stars but also rogue planets, planets that have been ejected from their star systems and drift through interstellar space. These rogue planets, which do not orbit any star, were once thought to be rare, but recent estimates suggest that there could be more rogue planets in our galaxy than stars. Some of these rogue planets may retain enough internal heat to support subsurface oceans, and studying them could reveal new environments where life could potentially exist. While the discovery of planets and moons continues to dominate headlines, astronomers are also making exciting advancements in our understanding of the universe's large-scale structure, particularly in the study of galaxy clusters. Galaxy clusters, which contain hundreds or even thousands of galaxies bound together by gravity, are some of the largest structures in the universe. Recent surveys have provided new insights into the behavior of these clusters, including the discovery of cold fronts in the hot gas that fills the space between galaxies. Cold fronts are sharp boundaries between regions of hot and cooler gas within galaxy clusters, and they are thought to be created by the motion of galaxies through the cluster or by mergers between clusters. These cold fronts can extend for millions of light years and provide clues about the dynamics of galaxy clusters, including the role of dark matter in shaping their structure. The study of galaxy clusters also has implications for our understanding of dark energy, as the expansion of the universe affects the growth and distribution of these massive structures over time. At the same time, astronomers are using gravitational lensing to map the distribution of dark matter within galaxy clusters. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster, bends the light from more distant objects, creating distorted or magnified images. By studying these distortions, scientists can create detailed maps of the dark matter in galaxy clusters, providing new insights into how dark matter interacts with normal matter and influences the growth of cosmic structures. As our ability to observe the universe improves, we are beginning to piece together a more complete picture of how galaxies, stars, and planets form and evolve over cosmic time. From the discovery of exotic objects like quark stars and rogue planets, to the study of planetary migration and the search for habitable exomoons, the universe is revealing itself to be far more complex and dynamic than we ever imagined. With each new discovery, we are reminded that the cosmos is full of surprises, and the next great breakthrough could be just around the corner. The upcoming generation of telescopes, space missions, and detectors promises to revolutionize our understanding of the universe, offering new opportunities to explore the most fundamental questions of existence. As we continue our journey through the cosmos, we are not only discovering new worlds and phenomena, but also deepening our understanding of the universe and our place within it. As we continue to venture into the unexplored realms of the cosmos, the universe's astonishing complexity grows more evident with each new discovery, bringing us closer to solving some of the most profound mysteries while revealing entirely new questions. One of the most recent and fascinating areas of research involves cosmic dawn, the period when the first stars and galaxies began to form, ending the cosmic dark ages that followed the Big Bang. This era marks a turning point in the universe's history, and recent observations are providing some of the clearest glimpses yet into how the universe transitioned from a dark, featureless expanse into the complex structure of stars, galaxies, and ultimately life as we know it. The discovery of galaxies and stars that formed in the universe's infancy, less than 1 billion years after the Big Bang, has been a breakthrough for astronomers. The James Webb Space Telescope (JWST) is poised to revolutionize our understanding of this period, as its infrared instruments are designed to detect the faint light from some of the earliest galaxies. Observing this light, which has been stretched to longer wavelengths by the universe's expansion, allows scientists to peer back to a time when the first atoms coalesced into stars and galaxies. By studying these primordial structures, we can learn about the processes that led to the formation of galaxies, stars, and ultimately planets. Recent discoveries have already pushed the limits of our understanding of the early universe. The detection of ultra-distant galaxies, some of which existed just 300 million years after the Big Bang, has challenged current models of galaxy formation. These galaxies appear to be much more massive and mature than expected, raising questions about how such large structures could have formed so quickly. One possible explanation is that the formation of these galaxies was driven by supermassive black holes, which could have rapidly accumulated mass and provided the gravitational pull necessary to form stars and galaxies in such a short time. The study of cosmic dawn is also shedding light on the reionization epoch, a period when the first stars and galaxies emitted enough radiation to ionize the surrounding hydrogen gas, effectively lighting up the universe. Before this period, the universe was filled with neutral hydrogen, which absorbed light and made it difficult for early galaxies to be observed. The process of reionization transformed the universe, allowing light to travel freely and making it possible for us to observe distant galaxies today. Understanding when and how reionization occurred is key to piecing together the timeline of the universe's evolution. The JWST, with its unparalleled sensitivity, will allow astronomers to directly observe the galaxies responsible for reionization, providing crucial data about the conditions of the early universe. These observations could answer fundamental questions about how the first stars formed, how galaxies assembled, and how the structure of the universe evolved over time. While the study of cosmic dawn offers insights into the earliest stages of galaxy formation, recent research has also focused on the other end of the cosmic timeline, the future of the universe. One of the most profound questions in modern cosmology concerns the ultimate fate of the universe, which is influenced by the mysterious force known as dark energy. Dark energy, which accounts for roughly 70% of the universe's total energy, is responsible for the accelerated expansion of the universe, and its nature remains one of the greatest unsolved mysteries in science. Recent observations suggest that the rate of cosmic expansion is not only continuing but accelerating, which has led to several competing theories about the universe's future. One of the leading ideas is the Big Freeze, in which the universe continues to expand indefinitely, eventually becoming cold and dark as galaxies move farther apart and stars run out of fuel. In this scenario, the universe would eventually reach a state of heat death, where all energy is evenly distributed and no further thermodynamic work can be done. Another possibility is the Big Rip, in which the expansion of the universe accelerates to the point where it tears apart galaxies, stars, and even atoms. This scenario is driven by the idea that dark energy could become increasingly dominant over time, causing the expansion rate to grow exponentially. If this happens, the fabric of space itself could be torn apart in a dramatic end to the universe. A third theory is the Big Bounce, which suggests that the universe could one day stop expanding and begin contracting, eventually collapsing in on itself in a big crunch, only to rebound in another Big Bang. This cyclical model posits that the universe goes through endless cycles of expansion and contraction, and we are currently in one of many such phases. The study of dark energy is critical to understanding which of these scenarios, if any, will unfold. Recent surveys, such as the Dark Energy Survey, DES, and upcoming missions like the Euclid satellite, are focused on mapping the distribution of galaxies and measuring the expansion of the universe with unprecedented precision. These observations could provide crucial data about the nature of dark energy and help determine whether the universe will end in a big freeze, a big rip, or some other as yet unimagined fate. While dark energy poses some of the deepest questions about the universe's long-term future, the study of black holes continues to offer remarkable insights into some of the universe's most extreme environments. One of the most exciting recent developments in black hole research is the detection of intermediate mass black holes, IMBHs, which bridge the gap between stellar mass black holes and supermassive black holes. Until recently, black holes were thought to exist primarily in two categories: stellar mass black holes, formed from the collapse of massive stars, and supermassive black holes, found at the centers of galaxies. The discovery of intermediate mass black holes, ranging from hundreds to thousands of times the mass of the Sun, has filled in a missing piece in the puzzle of black hole formation. IMBHs are thought to form through the mergers of smaller black holes or through the collapse of massive clouds of gas in the early universe. The detection of these black holes has raised important questions about how they grow and whether they might serve as the seeds from which supermassive black holes formed in the early universe. One of the most remarkable recent detections involved a black hole merger that produced a black hole with a mass of 150 times that of the Sun, far larger than any previously observed stellar mass black hole. This discovery, made through gravitational wave observations, provides strong evidence for the existence of IMBHs and offers new insights into the processes that drive black hole growth. At the same time, the study of supermassive black holes continues to advance, with new observations revealing the intricate dynamics of these cosmic giants. One of the most exciting discoveries in this area is the detection of relativistic jets, beams of charged particles traveling at nearly the speed of light, emanating from the regions around supermassive black holes. These jets, which can extend for thousands of light years, are among the most energetic phenomena in the universe, and they play a crucial role in regulating the growth of galaxies by blowing out gas and limiting star formation. The Event Horizon Telescope, EHT, which famously captured the first-ever image of a black hole's event horizon in 2019, is continuing to push the boundaries of what we can observe. Future observations with the EHT are expected to provide even more detailed images of black holes, including movies of how matter swirls around the event horizon before being consumed by the black hole. These observations could provide critical insights into the behavior of matter in the most extreme gravitational fields and help test Einstein's theory of general relativity in unprecedented ways. While the study of black holes and the universe's ultimate fate may seem distant from everyday concerns, recent advances in space exploration are bringing us closer to answering one of humanity's oldest questions: are we alone in the universe? The search for life beyond Earth has taken on new urgency with the discovery of potentially habitable exoplanets and the detection of organic molecules in unexpected places, such as Saturn's moon Enceladus and Jupiter's moon Europa. These icy moons, which are believed to harbor subsurface oceans beneath their frozen surfaces, are among the most promising places to search for life in our solar system. Recent observations of Enceladus's plumes, geysers of water vapor erupting from cracks in the moon's icy crust, have revealed the presence of organic molecules, providing tantalizing hints that life could exist in the moon's hidden ocean. Similarly, Europa's subsurface ocean is thought to contain more water than all of Earth's oceans combined, and upcoming missions, such as NASA's Europa Clipper, aim to investigate whether the conditions there could support life. Meanwhile, the search for habitable exoplanets continues to accelerate, with the discovery of thousands of planets orbiting distant stars. Among these, the discovery of Earth-sized planets in the habitable zones of their stars, where liquid water could exist, has reignited the search for biosignatures, such as oxygen or methane, in the atmospheres of these distant worlds. The James Webb Space Telescope, JWST, is expected to play a critical role in this search, with its ability to analyze the atmospheres of exoplanets in unprecedented detail. One of the most exciting recent discoveries is the detection of Proxima Centauri b, an Earth-sized planet orbiting in the habitable zone of the nearest star to our solar system. While Proxima b is subjected to intense radiation from its parent star, some scientists believe that it could still retain an atmosphere and possibly liquid water, making it one of the best candidates for the search for life beyond Earth. As we look to the future, the rapid pace of discovery in astronomy and space exploration promises to revolutionize our understanding of the universe. From the earliest moments of cosmic dawn to the ultimate fate of the cosmos, from the detection of intermediate mass black holes to the search for life on distant exoplanets, each new breakthrough brings us closer to answering some of the most profound questions about the nature of existence. The journey is far from over, and the next generation of telescopes, space missions, and gravitational wave detectors will undoubtedly uncover even more astonishing secrets of the universe, forever changing our understanding of reality. As we continue our journey through the universe's mysteries, each discovery pushes us further into the unknown, revealing both profound knowledge and deeper questions. One of the most groundbreaking revelations in recent years has been the detection of gravitational waves, a phenomenon predicted by Einstein's theory of general relativity more than a century ago. Since their first direct observation in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, gravitational waves have opened an entirely new way of observing the universe, one that does not rely on light, but instead on ripples in the very fabric of space-time. This has allowed us to listen to cosmic events that were previously invisible to traditional telescopes. These ripples are produced by some of the most violent and energetic events in the cosmos, such as the merging of black holes and neutron stars. The first detected signal came from a merger of two black holes, marking the beginning of a new era in astronomy. Since then, numerous gravitational wave events have been observed, providing a wealth of information about the universe's most extreme environments. One of the most exciting aspects of gravitational wave astronomy is its ability to detect events that are completely dark, meaning they emit no electromagnetic radiation, such as black hole mergers. Gravitational waves have also allowed scientists to observe events they had never expected to see, such as the merger of a black hole and a neutron star. This type of collision, detected for the first time in 2020, offers a rare opportunity to study the dynamics of both black holes and neutron stars in a single event. These mergers are particularly important because they provide insights into the behavior of matter under the most extreme gravitational conditions, potentially revealing clues about the fundamental nature of space-time and gravity itself. One of the most remarkable aspects of gravitational wave astronomy is its potential to answer fundamental questions about the origin of the universe. For example, scientists are now investigating whether primordial black holes that formed shortly after the Big Bang, might be responsible for some of the gravitational wave signals we detect. If primordial black holes exist, they could offer insights into the conditions of the early universe and potentially even shed light on the nature of dark matter. Some theories suggest that dark matter could be made up of these ancient black holes, which would have formed during the universe's first few moments of existence. In addition to detecting gravitational waves from black hole and neutron star mergers, scientists are now working to detect the subtle gravitational waves produced by the mergers of supermassive black holes. These cosmic giants, which can have masses millions or even billions of times that of the Sun, are thought to reside at the centers of most galaxies. When galaxies merge, their central black holes are expected to collide and form even larger black holes, releasing enormous amounts of energy in the form of gravitational waves. Detecting these signals, however, requires instruments far more sensitive than LIGO or Virgo, leading to the development of the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector. LISA, scheduled to launch in the 2030s, will be capable of detecting gravitational waves from supermassive black hole mergers across the universe. Unlike ground-based detectors, which are limited by noise and Earth's seismic activity, LISA will operate in the quiet environment of space, allowing it to detect much lower-frequency gravitational waves. This will enable scientists to study the merging of supermassive black holes, providing direct insights into the processes that shape galaxies over billions of years. While gravitational wave astronomy opens a new window on the universe's most violent events, another field that has seen dramatic advancements is the study of fast radio bursts, FRBs, brief, intense bursts of radio waves originating from distant galaxies. First discovered in 2007, FRBs remain one of the most mysterious phenomena in astronomy. These bursts last only milliseconds but release more energy in that brief time than the sun emits in an entire day. The origins of FRBs are still unknown, though recent discoveries are beginning to provide clues. In 2020, astronomers made a major breakthrough when they traced an FRB to a magnetar within our own galaxy. Magnetars are highly magnetized neutron stars, and they are known for producing powerful bursts of X-rays and gamma rays. The discovery of an FRB originating from a magnetar suggests that at least some FRBs could be caused by magnetar outbursts, where the intense magnetic fields release enormous amounts of energy. However, this explanation may not account for all FRBs, as many of them originate from much farther away, outside our galaxy, and some FRBs are repeating, while others are one-off events. Another tantalizing possibility is that FRBs might be caused by interactions between black holes and neutron stars, or even by exotic objects such as cosmic strings, hypothetical one-dimensional defects in space-time. There is also speculation, though highly controversial, that FRBs could be the result of advanced alien technology. While this explanation is far from proven, the mysterious and energetic nature of FRBs has made them a prime target for those searching for technosignatures, signals that could indicate the presence of intelligent civilizations. The ongoing study of FRBs has also opened the door to using them as cosmological tools. Because FRBs travel through vast distances in space, their signals are influenced by the material they pass through, including intergalactic gas and magnetic fields. By studying how FRBs are dispersed as they travel, astronomers can learn more about the structure of the universe and the distribution of matter between galaxies. This could provide new insights into the missing baryon problem, the mystery of where much of the universe's normal matter seems to be hiding. As we explore these enigmatic bursts of energy, another profound area of research focuses on the origin of life itself. Astrobiologists are increasingly turning their attention to icy moons in our solar system, such as Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. These moons are believed to have vast oceans of liquid water beneath their icy crusts, kept warm by tidal heating from their parent planets. In recent years, plumes of water vapor have been detected erupting from the surface of both Europa and Enceladus, providing direct evidence of subsurface oceans and offering tantalizing clues about the potential for life in these hidden environments. The discovery of complex organic molecules in the water vapor plumes of Enceladus has further fueled speculation that life could exist in these alien oceans. These molecules, along with the presence of water, energy sources such as hydrothermal vents, and essential chemical elements, make Enceladus and Europa two of the most promising candidates in the search for extraterrestrial life in our solar system. NASA's Europa Clipper mission, set to launch in the 2020s, will conduct detailed flybys of Europa, analyzing its icy surface and subsurface ocean for signs of habitability. If life exists in these hidden oceans, it could resemble the extremophiles found around hydrothermal vents on Earth, where life thrives in complete darkness under extreme pressure. Meanwhile, the study of exoplanets continues to advance at a rapid pace, with thousands of planets outside our solar system now confirmed. The discovery of Earth-like planets in the habitable zones of their stars has generated enormous excitement in the search for life. Among the most promising exoplanets is TRAPPIST-1e, an Earth-sized planet located in the habitable zone of a nearby star system. TRAPPIST-1e is part of a system of 7 rocky planets, 3 of which are located in the habitable zone, where liquid water could exist. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, will soon allow scientists to study the atmospheres of these exoplanets in greater detail than ever before. By analyzing the light passing through these atmospheres as the planets transit in front of their stars, astronomers can look for biosignatures such as oxygen, methane, and water vapor, gases that could indicate biological processes. The detection of such gases would represent a major breakthrough in the search for life beyond Earth. As we search for life in other star systems, we are also discovering new insights about the potential habitability of rogue planets. Planets that have been ejected from their star systems and now drift through interstellar space. These planets, once thought to be barren and inhospitable, could retain enough internal heat from radioactive decay or gravitational interactions to support subsurface oceans, similar to Europa and Enceladus. The discovery of rogue planets, particularly those with Earth-like masses, has expanded the range of environments where life could potentially exist. While we continue to search for life beyond Earth, scientists are also investigating the possibility that life could have originated elsewhere in the universe and spread to Earth via a process known as panspermia. According to this theory, life could have been transported to Earth by comets, asteroids, or other celestial objects, seeding our planet with the building blocks of life. The discovery of complex organic molecules in comets and the detection of amino acids in meteorites lend some credence to this idea, suggesting that the raw ingredients for life could be widespread throughout the universe. The exploration of the cosmos, from gravitational waves to exoplanets, from fast radio bursts to the search for life on icy moons, is rapidly transforming our understanding of the universe and our place within it. As new telescopes, detectors, and space missions come online, the pace of discovery is accelerating, and we are on the cusp of answering some of the most fundamental questions about existence. Are we alone in the universe? What is the ultimate fate of the cosmos? How did life begin, and where else might it exist? The journey toward these answers is just beginning, and each new discovery brings us one step closer to unlocking the universe's deepest secrets. The future of exploration promises to be as awe-inspiring as it is transformative, as we continue to push the boundaries of knowledge in our quest to understand the cosmos. As our exploration of the cosmos presses onward, the universe continues to reveal itself in increasingly unexpected ways, challenging what we know about reality and inspiring new questions about the nature of existence. One of the most astonishing recent developments is the growing understanding of time dilation on cosmic scales. This phenomenon, a direct consequence of Einstein's theory of relativity, has recently been observed in distant galaxies and black hole systems, revealing just how profoundly space and time are intertwined in the universe's most extreme environments. Time dilation occurs when massive gravitational fields slow down the passage of time, or when objects approach the speed of light. The greater the gravitational force or speed, the slower time moves relative to an outside observer. This effect has been measured near Earth, where satellites must account for slight time differences due to Earth's gravity, but it becomes far more dramatic around massive objects like black holes. Recent observations have begun to capture the effects of time dilation near the event horizons of supermassive black holes, where time practically comes to a standstill relative to distant observers. In 2019, researchers observed a unique event, a star passing close to the supermassive black hole at the center of our galaxy, Sagittarius A star. As the star neared the black hole, its light was stretched to longer wavelengths due to gravitational redshift, a consequence of time dilation. This phenomenon offered one of the clearest real-world examples of Einstein's theory of relativity playing out on such a vast scale. Observing these effects not only confirms the predictions of general relativity, but also offers insights into the behavior of matter and light near the most extreme gravitational fields in the universe. Time dilation also plays a critical role in understanding distant galaxies, especially when observing objects near the cosmic horizon, the furthest regions of the observable universe. Because the universe is expanding, galaxies at extreme distances are receding from us at speeds approaching the speed of light. As a result, time appears to slow down for these distant galaxies, meaning that events such as supernovae take longer to unfold from our perspective. Recent observations using powerful space telescopes have allowed astronomers to detect this time dilation effect in distant galaxies, providing new insights into the history of the universe's expansion and confirming the predictions of cosmological models. While time dilation reveals the intricacies of the universe's relationship with gravity and speed, another discovery is reshaping our understanding of the fundamental forces that govern the cosmos. The detection of high-energy neutrinos originating from distant astrophysical sources. Neutrinos, sometimes referred to as ghost particles because they interact so weakly with matter, are produced in some of the universe's most extreme environments, such as supernovae, gamma-ray bursts, and the accretion disks around black holes. In 2017, a major breakthrough occurred when the IceCube Neutrino Observatory, located deep in the ice of Antarctica, detected a high-energy neutrino that could be traced back to a blazar, a supermassive black hole at the center of a distant galaxy, emitting powerful jets of particles. This was the first time a high-energy neutrino had been linked to a specific astrophysical source, marking a significant step forward in our understanding of these elusive particles and the violent cosmic events that produce them. The detection confirmed that blazars and other extreme cosmic objects are capable of accelerating particles to incredibly high energies, far beyond anything achievable by human-made particle accelerators. Neutrino astronomy is still in its infancy, but the potential is enormous. Unlike photons, light particles, which can be blocked or absorbed by matter, neutrinos can pass through entire galaxies without being scattered or absorbed. This means they can carry information from deep inside stars, black holes, and other extreme environments that are otherwise inaccessible to traditional telescopes. As neutrino detectors become more sensitive, scientists hope to use neutrinos to study everything from the formation of supermassive black holes to the inner workings of supernovae. This new way of observing the universe will complement traditional astronomy, allowing us to explore the cosmos in ways that were once thought impossible. While neutrino astronomy offers a glimpse into some of the universe's most energetic events, another area of research is pushing the boundaries of our understanding of matter itself. The search for dark matter. Dark matter, which makes up roughly 85% of the matter in the universe, continues to elude direct detection despite decades of research. However, recent experiments have begun to narrow the possibilities for what dark matter might be, and new detection methods are offering hope that we may be on the verge of discovering this mysterious substance. One of the most promising avenues of research involves the detection of axions, hypothetical particles that could make up dark matter. Axions are incredibly light and weakly interacting particles, making them extremely difficult to detect, but new experiments are being designed specifically to hunt for them. The Axion Dark Matter Experiment, ADMX, for example, is using sensitive detectors to search for signs of axions converting into photons in the presence of a magnetic field. If axions exist, detecting them would not only solve the mystery of dark matter, but also have profound implications for particle physics and our understanding of the universe's structure. Another potential dark matter candidate is the sterile neutrino, a hypothetical type of neutrino that does not interact with ordinary matter except through gravity. Sterile neutrinos would be extremely difficult to detect, but could explain the abundance of dark matter in the universe. Several experiments are currently searching for evidence of sterile neutrinos, and the discovery of such particles would open up an entirely new frontier in particle physics, potentially revolutionizing our understanding of the universe's fundamental building blocks. While the search for dark matter continues, researchers are also exploring new ways to study dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy remains one of the most profound mysteries in cosmology, accounting for roughly 70% of the universe's total energy content. Recent surveys, such as the Dark Energy Survey and the upcoming Euclid mission, are focusing on mapping the distribution of galaxies and measuring the universe's expansion rate in unprecedented detail. One of the most intriguing possibilities is that dark energy could be related to a previously unknown field or force in physics, something that exists on cosmic scales but does not interact with matter in the way we are familiar with. Some theories suggest that dark energy could be a manifestation of a fifth force, beyond the four known fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Others propose that dark energy could be explained by modifications to general relativity or the existence of extra dimensions, ideas that push the boundaries of theoretical physics. As astronomers and physicists search for answers to these profound questions, advancements in space exploration are continuing to reshape our understanding of the solar system and beyond. The recent success of the Mars Perseverance rover has provided a wealth of data about the red planet, including evidence that Mars once had liquid water and potentially habitable conditions billions of years ago. Perseverance is currently exploring the ancient river delta in Jezero crater, searching for signs of past microbial life and collecting rock samples that will eventually be returned to Earth by future missions. One of the most exciting aspects of the Perseverance mission is its ability to identify and collect samples that could contain biosignatures, chemical signs of life. The discovery of ancient microbial life on Mars would represent a monumental breakthrough, proving that life is not unique to Earth and potentially offering insights into how life arose in the solar system. The upcoming Mars Sample Return mission, which will retrieve samples collected by Perseverance, will allow scientists to analyze Martian material in laboratories on Earth, providing the highest level of precision in the search for life. Meanwhile, the study of other ocean worlds in the solar system, such as Europa and Enceladus, continues to offer promising avenues for discovering extraterrestrial life. These icy moons are believed to harbor vast subsurface oceans beneath their frozen surfaces, and recent observations have revealed the presence of organic molecules in the water plumes erupting from Enceladus. NASA's Europa Clipper mission, scheduled for launch in the 2020s, will conduct detailed flybys of Europa, studying its icy shell and ocean for signs of life. At the same time, the search for life beyond our solar system has accelerated with the discovery of thousands of exoplanets, many of which are located in their stars' habitable zones. One of the most exciting exoplanets discovered in recent years is Proxima Centauri b, which orbits the closest star to our solar system. Proxima b is located in the habitable zone of its star, meaning it could potentially support liquid water on its surface. While Proxima b is subject to intense stellar flares, some scientists believe it could retain an atmosphere capable of protecting the planet from radiation, making it one of the best candidates for the search for life beyond Earth. The James Webb Space Telescope (JWST), once operational, will play a key role in studying the atmospheres of potentially habitable exoplanets. By analyzing the light that passes through these planets' atmospheres as they transit in front of their stars, JWST will be able to detect gases like oxygen, methane, and water vapor, potential indicators of life. The discovery of biosignatures on an exoplanet would represent one of the most profound discoveries in the history of science, providing the first direct evidence that life exists beyond Earth. As we continue to push the boundaries of exploration and knowledge, the universe reveals itself to be more complex and wondrous than we could have ever imagined. From the detection of gravitational waves and high-energy neutrinos to the search for dark matter and the study of exoplanets, each new discovery brings us closer to answering some of the most profound questions about the nature of reality, the origins of life, and our place in the cosmos. The future of space exploration and astronomy promises to be as exciting as it is transformative, with new technologies and missions poised to uncover even more of the universe's secrets. Whether we are exploring the behavior of matter near black holes, searching for life on distant worlds, or investigating the fundamental forces that govern the universe, the journey ahead is filled with discoveries that will reshape our understanding of existence. The universe, in all its vastness and mystery, continues to inspire awe, wonder, and the unrelenting drive to explore what lies beyond. As humanity continues its tireless exploration of the cosmos, the next steps promise to be even more remarkable than those that have come before. The ever-expanding horizon of space research is yielding insights not only about distant galaxies and mysterious forces like dark energy, but also about the deep, uncharted realms within our own solar system. One of the most recent and exciting breakthroughs centers around the ongoing study of ocean worlds, moons and planets that may have vast oceans hidden beneath their surfaces. These discoveries have opened up new possibilities for the search for life beyond Earth, dramatically reshaping our understanding of where life might exist in the universe. One of the most intriguing ocean worlds is Saturn's moon Enceladus. Since the Cassini spacecraft first detected water ice plumes erupting from Enceladus's south pole, scientists have been captivated by the possibility that this small, icy moon might harbor the conditions necessary for life. Beneath its thick ice crust, Enceladus is thought to contain a global subsurface ocean heated by tidal forces generated by Saturn's immense gravity. This heating may produce hydrothermal activity at the ocean floor, similar to the environments around Earth's deep-sea hydrothermal vents, where life thrives without sunlight. Recent studies of the water plumes have revealed that Enceladus's ocean contains a variety of organic molecules, including some that are considered key building blocks of life, such as methane. The discovery of these molecules has fueled speculation that microbial life could exist in the moon's dark, cold ocean, sustained by the chemical energy produced by hydrothermal vents. NASA's proposed Enceladus Life Finder (ELF) mission, if approved, would perform detailed flybys of the moon, sampling its plumes to search for direct evidence of life. Another key ocean world in the spotlight is Jupiter's moon Europa, which also has a subsurface ocean beneath a thick layer of ice. Like Enceladus, Europa's ocean is kept warm by tidal forces from its parent planet, and it may also have hydrothermal activity on its ocean floor. Europa's icy surface is riddled with cracks and ridges, suggesting that liquid water occasionally reaches the surface through these fractures. NASA's upcoming Europa Clipper mission is designed to study the moon in unprecedented detail, using radar to penetrate the ice and determine the thickness of the crust, as well as sampling the chemistry of the surface for signs of habitability. Europa and Enceladus are not the only ocean worlds being considered as candidates for extraterrestrial life. Titan, Saturn's largest moon, also holds significant potential for exploration. Titan is unique because it is the only known moon with a dense atmosphere and liquid bodies on its surface, lakes and seas of methane and ethane. While these hydrocarbon lakes are unlikely to support life as we know it, Titan's surface environment, combined with the possibility of a subsurface ocean of water and ammonia, makes it a fascinating target for astrobiological study. NASA's Dragonfly mission, set to launch in the mid-2020s, will send a rotorcraft to Titan's surface to explore its organic-rich environment and search for prebiotic chemistry. While the study of ocean worlds within our own solar system is capturing the imagination of scientists and the public alike, the search for life beyond our solar system is accelerating at a breathtaking pace, thanks to the discovery of thousands of exoplanets. One of the most exciting areas of exoplanet research involves the detection of super-Earths, rocky planets larger than Earth but smaller than Neptune, some of which may reside in the habitable zones of their stars. These planets have the potential to support liquid water on their surfaces, and their relatively large sizes make them easier to detect and study than smaller Earth-sized planets. Among the most promising super-Earths discovered in recent years is LHS 1140b, a rocky planet located about 40 light-years from Earth. LHS 1140b is slightly larger and more massive than Earth and orbits within the habitable zone of a nearby red dwarf star. This planet is particularly interesting because its density suggests it has a solid, rocky composition, and its distance from its star means it could potentially support liquid water. Future observations with the James Webb Space Telescope, JWST, and other instruments will focus on analyzing the planet's atmosphere to search for signs of habitability, such as water vapor, carbon dioxide, or even biosignatures like methane or oxygen. Another super-Earth of great interest is Proxima Centauri b, which orbits the closest star to our solar system, Proxima Centauri. Located just over 4 light-years away, Proxima b resides in the habitable zone of its star, where temperatures could allow for liquid water to exist. However, Proxima Centauri is an active red dwarf star that emits powerful flares, which could strip away the planet's atmosphere and make it inhospitable to life. Nevertheless, if Proxima b has a strong magnetic field or a thick atmosphere, it might still retain conditions suitable for life. Upcoming observations will help determine whether the planet's atmosphere has survived and whether any biosignatures are present. While the discovery of potentially habitable exoplanets continues to captivate astronomers, a new and exciting frontier is emerging in the search for exomoons, moons that orbit planets outside our solar system. Until recently, detecting exomoons was thought to be extremely difficult, but advances in observational techniques have made it possible to search for these elusive objects. The discovery of the first exomoon candidate, orbiting a gas giant planet in the Kepler 1625 system, has raised the tantalizing possibility that many exoplanets could host moons, some of which might be even more likely to support life than the planets themselves. Exomoons could have diverse environments, from rocky, Earth-like surfaces to icy worlds with subsurface oceans, similar to Europa and Enceladus. If exomoons are common around gas giants in the habitable zones of their stars, they could represent an entirely new class of potentially habitable environments. The detection and study of exomoons could dramatically expand the number of places where life might exist, providing new targets in the search for extraterrestrial life. In addition to exomoons, astronomers are increasingly focusing on the search for biosignatures in the atmospheres of exoplanets. The detection of gases like oxygen, methane, and carbon dioxide in an exoplanet's atmosphere could provide strong evidence of biological activity. One of the most promising strategies for detecting biosignatures involves transit spectroscopy, where scientists analyze the light from a star as it passes through an exoplanet's atmosphere during a transit event. The James Webb Space Telescope and other next-generation observatories will be able to perform this type of analysis with unprecedented precision, potentially revealing the first signs of life beyond Earth. While the search for life elsewhere in the universe is accelerating, advances in space exploration closer to home are paving the way for humanity's next great leap, returning to the moon and sending humans to Mars. NASA's Artemis program aims to land the first woman and the next man on the moon by the mid-2020s, marking the first human visit to the lunar surface since the Apollo missions. Artemis will not only return astronauts to the moon, but also lay the groundwork for a sustainable human presence on the lunar surface, using resources like water ice found at the moon's poles to support long-term exploration. The knowledge gained from lunar exploration will be crucial for future missions to Mars. NASA and private companies like SpaceX are already planning crewed missions to the Red Planet, with the goal of establishing a permanent human settlement. One of the biggest challenges of living on Mars is its thin atmosphere, which offers little protection from radiation, as well as the lack of accessible resources. However, the discovery of water ice beneath the Martian surface provides a potential resource for drinking water, oxygen production, and even rocket fuel. If humans can learn to live sustainably on Mars, it could serve as a stepping stone for deeper space exploration, including missions to the outer planets and their moons. As humanity prepares to venture beyond Earth, another frontier of research is focusing on the role that artificial intelligence, AI, will play in future space exploration. AI is already being used to process vast amounts of data from space missions, helping scientists identify exoplanets, analyze the surface of Mars, and search for signs of life in complex data sets. In the future, AI systems could become indispensable for autonomous spacecraft, allowing missions to explore distant worlds without requiring constant input from Earth. AI could also assist in deep space navigation, resource management, and even building and maintaining habitats on the Moon or Mars. In tandem with AI, the development of advanced propulsion systems is essential for making interstellar travel a reality. Concepts such as nuclear propulsion, ion drives, and even warp drives are being explored as potential ways to dramatically reduce the time it takes to travel between stars. While faster-than-light travel remains speculative, breakthroughs in propulsion technology could one day enable humans to explore the nearest star systems within a human lifetime. As we stand on the precipice of these momentous advances in space exploration, it becomes increasingly clear that humanity's future lies in the stars. The discoveries we are making, whether it's the detection of potentially habitable exoplanets, the exploration of ocean worlds in our solar system, or the search for biosignatures on distant moons and planets, are expanding the horizons of what is possible and deepening our understanding of our place in the cosmos. Each new discovery brings us one step closer to answering some of the most profound questions. Are we alone in the universe? What is the true nature of life? And how far can humanity extend its reach among the stars? The future of space exploration is as limitless as the cosmos itself, and the next generation of explorers, scientists, and innovators will take us further than we ever dreamed possible. The journey to the stars is just beginning, and with it, the next chapter of humanity's story is waiting to be written one discovery at a time. As humanity continues its grand odyssey through the cosmos, the discoveries we are making are beginning to reshape the very fabric of how we understand the universe and our place within it. The advancements in space exploration, astrophysics, and cosmology are pushing us ever closer to finding answers to some of our most profound questions. From black holes and gravitational waves to the search for extraterrestrial life and the future of human colonization of space, the next chapter of space exploration is already unfolding with breathtaking speed. One of the most intriguing and actively researched phenomena today is the idea of quantum gravity. For decades, physicists have sought to reconcile the two pillars of modern physics: Einstein's general theory of relativity, which describes the force of gravity on cosmic scales, and quantum mechanics, which governs the behavior of the tiniest particles in the universe. These two theories, despite their individual successes, are fundamentally incompatible. General relativity breaks down at the quantum level, and quantum mechanics struggles to account for gravity's effects on large scales. Solving this riddle would create a theory of everything, uniting all the forces of nature into a single, coherent framework. One of the most promising approaches to understanding quantum gravity involves the study of black holes, which represent the ultimate test of both quantum mechanics and general relativity. At the heart of a black hole lies the singularity, a point of infinite density where our current understanding of physics breaks down. Understanding the singularity could provide key insights into how gravity behaves on the quantum level and potentially unlock the secrets of the universe's most fundamental forces. Recent research into the information paradox of black holes has also opened up new questions about the relationship between quantum mechanics and space-time itself. The paradox arises because, according to quantum mechanics, information about a system should never be lost, but black holes seem to erase information when they consume matter. However, recent developments in theoretical physics, particularly in the field of string theory, suggest that black holes may not actually destroy information, but instead encode it on their event horizons in ways we do not yet fully understand. This concept, known as the holographic principle, proposes that all the information contained within a volume of space can be represented on its boundary, much like a hologram. If true, this would have profound implications for our understanding of reality, suggesting that the universe itself may operate as a kind of cosmic hologram, with information encoded on the surface of space-time itself. The study of black holes, especially through gravitational wave observations, is also shedding light on the birth and death of stars, the formation of galaxies, and the evolution of the universe. With each new detection of gravitational waves, ripples in space-time caused by the merging of black holes and neutron stars, we are gaining unprecedented insights into the violent processes that shape the cosmos. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will be the first space-based gravitational wave observatory capable of detecting mergers of supermassive black holes and even the ripples from the earliest moments after the Big Bang. These observations will offer a new window into the universe's history, potentially answering questions about how galaxies formed and evolved, as well as providing a deeper understanding of dark matter and dark energy. Speaking of dark matter, one of the most significant ongoing scientific efforts is the attempt to directly detect and understand this mysterious substance. While dark matter makes up about 85% of the matter in the universe, it has so far eluded direct detection, revealing itself only through its gravitational effects on galaxies and clusters of galaxies. However, the recent development of more sensitive detectors, including the ongoing search for weakly interacting massive particles, WIMPs, and axions, has brought us closer than ever to uncovering the true nature of dark matter. At the same time, scientists are making strides in understanding dark energy, the even more mysterious force responsible for the accelerated expansion of the universe. New data from galaxy surveys and space missions such as the Dark Energy Survey (DES) and the upcoming Euclid mission are providing fresh insights into how dark energy influences the universe's large-scale structure. Some theories suggest that dark energy could be a manifestation of a new field of physics, perhaps a fifth force that operates on cosmic scales, or even a sign that general relativity needs to be modified on large scales. Whatever dark energy turns out to be, solving this mystery will have profound implications for our understanding of the universe's future and its ultimate fate. As we ponder the cosmic scale mysteries of dark matter and dark energy, another area of research is moving forward with remarkable momentum: the search for habitable exoplanets and extraterrestrial life. Thousands of exoplanets have been discovered, many of them in their stars' habitable zones where liquid water could exist. But the search for life is not just about finding planets similar to Earth. It's also about understanding the range of environments where life could potentially thrive. One of the most exciting developments in recent exoplanet research is the discovery of super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, which may have thick atmospheres and oceans that could harbor life. Recent observations with the Hubble Space Telescope and upcoming missions with the James Webb Space Telescope (JWST) are focused on analyzing the atmospheres of these planets, searching for biosignatures such as oxygen, methane, and water vapor. The detection of such gases would be a strong indicator of biological processes, potentially marking the first discovery of life beyond Earth. Another fascinating area of research is the study of rogue planets. Planets that do not orbit any star, but instead drift freely through interstellar space. While rogue planets were once thought to be barren, icy worlds, recent research suggests that some of them could retain internal heat generated by radioactive decay, allowing them to maintain subsurface oceans of liquid water. If life can exist in such environments, rogue planets could represent a new class of potentially habitable worlds, vastly increasing the number of places in the universe where life could exist. In tandem with the search for habitable planets, researchers are also investigating the possibility of finding biosignatures within our own solar system, particularly on the icy moons of the outer planets. Jupiter's moon Europa and Saturn's moon Enceladus are both believed to have subsurface oceans beneath their icy crusts, and recent data suggest that these oceans may contain the essential ingredients for life, such as water, organic molecules, and energy sources like hydrothermal vents. NASA's Europa Clipper mission, scheduled for launch in the 2020s, will perform detailed flybys of Europa, searching for signs of habitability in its icy shell and ocean. Enceladus, with its spectacular plumes of water vapor erupting from its south pole, is also a prime target in the search for life. Cassini's flybys of Enceladus revealed that these plumes contain organic molecules, providing tantalizing evidence that the moon's subsurface ocean could harbor microbial life. Future missions to Enceladus could analyze these plumes in greater detail, perhaps even capturing and returning samples to Earth for study. While the search for life beyond Earth is a key focus of current research, the next great challenge for humanity is the colonization of other worlds. The idea of humans living on the Moon, Mars, or even beyond has long been a staple of science fiction. But recent technological advancements are bringing this dream closer to reality. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, establishing a sustainable human presence on the lunar surface and using the Moon as a stepping stone for future missions to Mars. Mars remains the ultimate target for human exploration. With its thin atmosphere and extreme temperatures, Mars presents significant challenges for human habitation. But recent discoveries of water ice beneath the Martian surface provide hope that future explorers could use local resources to sustain long-term missions. Private companies like SpaceX are also pushing the boundaries of what's possible, with plans to send the first humans to Mars within the next decade. As humanity prepares to venture beyond Earth, the development of advanced propulsion technologies will be critical to making interstellar travel a reality. Concepts such as nuclear propulsion, ion drives, and even antimatter propulsion are being explored as potential ways to dramatically reduce travel time between the stars. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe, and see you on our next interstellar trip.